categorize them. So it's kind of complementary to what I talk about. It's not exactly the same. And you'll see today, what do I mean by compute models? It's how do you organize a computation, right? What are mental models you can use of how am I trying to do this and how am I trying to make it go fast? So if you want a complementary treatment of that, go read that chapter. I probably wouldn't get bogged down in the very end of it. The very end of it starts getting really detailed. That's fine. The questionnaire doesn't really ask you questions about that part of it. I'm going to release assignment 1 very soon, hopefully tomorrow. It's basically the hardware description language design of a simple computation in various compute styles. And it's due Sunday, October 5th, so you have almost 3 weeks to do it. Basically, part of this, again, is to teach you the CAD tools. So if you don't know Quartus, you don't know Model Sim, you don't know how to interpret a timing report, this is to guide you through all those things. And it's going to get you to employ 3 of the compute models that we talk about today, or kind of at least 3 variations of some of the compute models we talk about, to see, do they actually make any difference to efficiency? So those are kind of the 2 main purposes of this. Get you used to the CAD tools, and play with these different compute models to see, like, do they actually make a difference? There are a bunch of different versions of Quartus on the UG machines. So probably the easiest way to do this is to actually use the UG machines. You can physically use them. I'll also post a document on how to access them through VNC if you want to use them from home. There are lots of versions. If you use these scripts, Quartus.start to start the Quartus compiler and timing analyzer, etc. And Model Sim 18.start to start a simulator that you can use to verify your circuit is functionally correct. It's probably the easiest because those are the versions that I'm going to test everything with, or I am testing everything with. You can use any version you want. So if you want to use a different version, you want to install it on your home PC, that's all fine. It's just these are the ones that I'm testing myself to make sure they work. And the assignment handout will have information on all this. Like, you know, if you want to install Quartus, what do you do? Let's walk through these CAD tools, etc. So that's part of the purpose of it. Okay, so I'm giving you some skeleton code and a test bench in Verilog. So the easiest way to complete this assignment is in Verilog, although you could use VHDL if you wish. In case you don't know Verilog, so some people didn't know Verilog. What we use in our own undergrad program here is a widely used textbook written by 2 U of T profs, Steve Brown and Zvonko Vranacek. So you can get that out of the bookstore. There's a link to it. If you already know Verilog, you don't need this text, but it's a good reference if you don't know Verilog. You're going to notice that the test benches that I give you and the starter files end in .sv, which means system Verilog. System Verilog really just means the next generation of Verilog. They just gave it a fancy name instead of like a, V2 or something like that. If you want to know more about system Verilog, this is a set of lectures from UCSD that I found useful that basically goes from lecture 1 to lecture 4 of this course that the prof has kindly put online. It basically goes through the basics of, like, how do you describe different hardware with system Verilog. You don't need to know all this, and if you already know Verilog, you pretty much know it. But if you don't, this could be a useful resource. It also talks about a few things where system Verilog, this new version of Verilog, is a bit better than the old versions of Verilog that you might have learned in school. If you know a lot about HDL already, but you want to know more about best practices, Sutherland is a consultant. I actually forget what Sutherland's first name is again. But anyway, he's a consultant who has written a bunch of books on how to write HDL well. So these are much more advanced, but if you're kind of interested in exploring his website and the book he's written, it's a lot of, like, more advanced do's and don'ts. Well beyond what you need to know for this course, but might be interesting. And this link is an archive of papers from Cliff Cummings. So he's a well-known Verilog trainer, so he teaches people how to write really good Verilog, how to create modular, well-described hardware. So this talks about good coding styles, some gotchas, some advanced features. So again, well beyond what you need to know for this course. But if you're basically saying, well, I already know the basics, I'd like to see what more advanced things are out there, you could go check this out. Okay, so actually, I did this in the survey, so most people I think know Verilog. So how many people here know Verilog already? Okay, so most people, but there are some who don't. How many people already, when you learned Verilog, did you use System Verilog already? Okay, so now actually a reasonable number. So it used to be that wasn't very many at all. But how many people learned Verilog but not System Verilog? Okay, so a reasonable number too. So System Verilog adds a whole bunch of new features to Verilog. And a lot of them are for essentially simulation. So simulation is where you're writing code that you can use to model a hardware system, but you can't really synthesize it, meaning it's too abstract for a tool like Core to Serve Auto to turn into hardware. Okay, so we want to actually turn stuff into hardware. So we're not going to, we use a bit of that in the test bench, but we've written the test benches for you that will actually test your hardware. For the actual hardware you're writing, you're only using synthesizable constructs. So essentially the more simple parts of the language, which a tool like Quartus can actually turn into hardware. So that kind of pares down, what's new in System Verilog that we would care about. But there are a few new features beyond basic Verilog that are quite useful. So in Verilog, you had these always blocks that were, whenever something changes in this list of signals, activate this block and do something. System Verilog still has those, but you can now basically make blocks of code that are always COM or always flip-flop. And that's just better practice, right? When you're writing code that you want to be synthesized, you are normally saying this block of hardware should wake up when the clock changes, okay? So it's intended to model a flip-flop. And if you write always flip-flop, the tool will check that. If it finds that the way you wrote it, that's not true, it's going to say, well, you said you wanted flip-flops, and this doesn't actually match flip-flops. So it's a better way to write it. Always COMs means the opposite, right? The way you've written this block of code and the always block, it should wake up whenever a signal changes, which is what combinational logic does. Always COM means the tool will warn you if that's not the case. It's going to say, this is actually not combinational logic. So better to use those two things because it's more descriptive and you get some error checking. In Verilog, you probably remember that there's this set of rules for when you declare a variable, a signal, a wire, and when you declare it a reg. Does anybody remember this? Is this bringing back memories? Okay, those rules are bizarre, okay? Because they should not exist. They have no meaning from a hardware perspective. They basically exist because of the way the original Verilog simulators were written. They were basically writing wire or reg to tell the simulator how it should allocate storage in the simulator for this variable or not. It had no real meaning from a hardware intent point of view, and you had to actually just follow certain rules or it wouldn't compile. So that's kind of insane, right? Where you say, I have two different syntaxes, and you must use this one in this case and that one in that case. So what System Verilog does is you can still use wire and reg, but you can now just declare everything logic. And logic means it's just logic, right? It could be a register, it could be a connection, it is some signal, and you don't have to worry about it. So you can just, whatever rules you learned for the exam of Verilog in your undergrad, you can just forget them if you just always use logic. So that's what I do. Okay, so as I said, I'll release the assignment soon. In the marking rubric, you'll see that there's a small amount of marks for the quality of the code you write. So comment your code. If you need states, for example, instead of just you're checking for binary value 0, 1, 2, 3, give the states names, right? So you can use enumerated types or parameters if you're not quite sure how to do that. Where was it? The textbook that I pointed at, and one link back here, this one, will show you how to do it, okay? And a web search will also show you how to do it. But basically, that's a lot easier to read. Don't make duplicated code, okay? So factor out into a module that you instantiate multiple times. It's probably the most powerful technique. You can also, if you have repeated code over and over again, you can use a generator for loops and use meaningful names, okay? So I don't want to see a lot of names that are like R, I, O, K, right? You should use longer names, make sure they're pretty self-documenting. So we're not looking for anything super fancy in code, just follow some basic rules. Okay, so the assignment that you're going to do is a computation circuit. It's pretty simple. You're approximating an exponential. using a Taylor series. So it just makes you, you've got a few steps in your computation, you're going to try to make it fast, you're going to see how efficient it is in a few different compute styles. And you're going to show that you can make it work. We're doing this in fixed point numbers. Okay, so you can read the slide, but how many people already know what a fixed point number is? Okay, so how many people don't know what a fixed point number is? Okay, so at least some people don't know what it is, and there's always like that mysterious group who will not respond, right? They're like, that is my private information, right? It's like I'm asking for your banking PIN code. Okay, so a fixed point number is basically an integer. It's an integer which we interpret as a fractional number. So you get to use all the standard integer hardware, which is very efficient. You just remember where the decimal point should be. Okay, so if we take a 16-bit signed integer, right, we can represent numbers from negative 65,000 to basically positive 65,000. And our precision, the space between numbers, is 1, right? Now that might match exactly what we want to do, but sometimes we might be working with numbers that are in a smaller range, but we want more precision. So in this lab, the input you're getting actually has 2 integer bits. Okay, so it's going to be a number between 0 and about 2, right? So from about -2 to +2, because these are signed numbers. And we're representing the numbers much more precisely. The distance between values is 2 to the -14. So you're basically getting relatively small numbers coming in, and you're computing their exponential. We don't care about the exponential of some of these huge numbers. We only want it, our inputs are going to be in a pretty limited range. So we're interpreting our 16-bit numbers as having 2 bits to the left of the decimal place and 14 to the right of the decimal place. Does it make sense? So how do we work with those? Basically, you just declare them as, you work them as integers, and you just remember where the decimal point would be. So if you want to add, subtract, multiply, you just use the normal integer methods. So in Verilog, you can say like times, you can say plus, and it will add them or multiply them. It doesn't care that they're fixed points. It's just doing the same thing as it would do for any vector of bits, like any integer. You have to, in your code, like as you're designing things, you keep track of where the decimal point is. So at some point, you're going to interpret the numbers when you output them, or when you decide you're going to round off and throw away some bits. So you need to be keeping track of where the decimal point is. So the format that you're getting an input is, we usually use this term, this letter Q, to indicate something that's fixed point. So it's Q2.14. So 2 bits to the left of the decimal point, 14 to the right. So it's a 16-bit number. If you take 2 of those numbers and add them together, you get a 17-bit number, right? You need 17 bits to add these and make sure you don't get overflow. The decimal point doesn't move. So the output would be a Q3.14 number. Does that make sense? Okay, if you multiply them, so you take 2 of these Q2.14 numbers. Okay, if I multiply 2 16-bit numbers, I actually get a 32-bit output. And that 32-bit output would actually have 4 bits to the left of the decimal point. Okay, so if I multiply numbers that are as big as like +2, I could get a number as big as +4. If I multiply -2 times +2, I could get a number as small as -4. I actually need 4 bits to represent that as a signed number. So I've got Q4, and then the other bits are all to the right of the decimal point. Okay, so it's just a 32-bit output, but notice that the decimal point, it kind of moved a bit, right, when I did the multiply. But the place it moved is logical. Basically, my output is twice as wide as my input was. My decimal point divides things in the same way. So you can kind of work that out in your head in many different ways, but that's what you're going to get in terms of where the decimal point is after a multiply. As you do repeated adds and multiplies, you might get a lot of fractional bits if you just keep all of the bits that come out of every multiply. So for assignment 1, the input is in Q2.14 format, so 16-bit inputs. Your output's a little more precise. You're going to multiply and add some numbers, so we're not going to make you put it out in 16 bits. Not quite accurate enough, but it is accurate enough to do Q7.25. Okay, so you're going to be adding things up, multiplying, keeping track of where the decimal point is. You can keep your internal precision, bigger, but when you output it, this is the part we want. Okay, so if you have like 60 decimal points, we don't want them all. We only want the last 25. If you actually had 15 digits to the left of the decimal point, again, we don't want them all. We just want the low order 7 bits. That's enough to represent the output. Does that make sense? Okay. And we give you a test bench, so you start off by just like confirming everything's correct. Make sure you get all the right outputs, and then you can start optimizing. Okay, so why not just use floating point? And let's just do a review of what floating point is. So this is a 16-bit floating point. Because I was using a 16-bit integer there, the competing format would be 16-bit floating point. So we've got 1 bit for the sign. We have a 5-bit exponent. And then we have 10 bits for the mantissa, which is basically like the kind of normal number. And the way floating point works is we take the sign bit. So this is either positive or negative 1. That's the way we interpret this. Times, so don't interpret that as like 0 or 1. Interpret it as positive or negative 1. Times the exponent. You bias the exponent. Okay, so this exponent goes from 0 to 30. Let me think about this actually. 2 to the 5th is, so from 0 to 31. I actually don't want exponents from 0 to 31. Usually you want to have some negative exponents for small numbers, some positive exponents for big numbers. So the IEEE 16-bit floating point uses a 15, exponent bias of 15. So you take that number, subtract 15, and you say 2 to the that. Okay? And then we take these 10 bits of mantissa, and we say, well, there should always be a 1 in front of them, because floating point numbers, we've got this exponent to shift around where the number is. So we'll always say that it starts with a 1, but we won't store it. So it's 1 dot, there's 10 bits of mantissa. Okay, so that's our format. How many people actually already know all this about floating point? Okay, it's quite a few. How many people actually learned something from that? So I'll cut it next year if I don't. Okay, a few, so I'm happy with that. Okay, so positives, the range is larger than fixed point. This exponent means we can represent a wide range of very small and very big values. So a lot of numbers near 0 and a lot of really big values. So if you need a large numeric range, it's a better choice. It's also, if you have no idea what your numeric range is, it's a bit easier, right? Like your odds of overflowing are much lower. So if you just go, I don't know, then this is a safer choice. But it has a smaller mantissa than equivalent fixed point. So basically, if you know your range is pretty limited, this exponent's not that useful, and essentially I lost fraction bits. So my gap between numbers is actually bigger. I've got a little bit less precision. So if I actually know a lot about my application, I may not like this trade-off numerically. I may be like, I know the numbers are actually in this range. I don't need this exponent. Give me more mantissa bits. That's effectively what fixed point does. But the other reason we're using fixed point is it's smaller, faster, and lower power. So in hardware, people do use floating point in hardware a lot. Okay, so it is increasingly used because it's kind of easier and it's also good for giving you a lot of range. But when they can, they do try to go to fixed point because it does save a lot of power. So I guess I told you some of the key applications of FPGAs are in communications, like base stations for cell phones. There's a lot of high-end FPGAs in them doing all sorts of signal processing. Almost all fixed point, okay? Because you're going to spend a lot of money on those base stations, and so they will optimize them heavily, and they have a pretty good idea, like they're willing to put in the effort to figure out, well, what is the value of the signals coming in off the antennas, and we will normalize them, and we'll be careful. They'll put that effort in, and they'll make sure it fixed in a fixed point range, and they'll do it efficiently. So why is fixed point smaller, faster, lower power? So you can kind of read it there. But anybody want to take it? Like, does it make sense that it's like fixed point is more efficient? Okay, so you're kind of nodding. So let's just walk through why. So if I was to add 2 fixed point numbers, I showed you how to do it. You just add them as if they were integers, which is pretty small hardware actually. You know how to build an adder. And then you just basically remember where the decimal point is. You don't even really make any hardware for that. You remember where it is in the next stage of your hardware. Okay, let's compare that to if I'm adding two floating point 16 numbers. And we'll say they're number 1 and number 2. And each of those has like, sign 1, sign 2, mantissa 1, mantissa 2, etc. Okay, so the first thing I have to do is I have to figure out what is the exponent of my output going to be. And that's going to be the maximum of the two input exponents. Okay, so I do that. I now need to add these two mantissas together, like the actual, 1.m. This is like my real number, right? After I've got the exponents lined up. Okay, so I want to add these two mantissas together, but if they have different exponents, I can't do that. So before I add the two mantissas together, I have to actually shift whichever one has a smaller exponent by this amount, whatever basically the bigger exponent minus the smaller exponent. I have to line up the mantissas so that they now both are represented with the same exponent. Okay, I put my 1s in. So I put the 1 in front of the mantissa from the larger exponent number. I put the 1 in front of the mantissa of the smaller exponent number, and I shift that one. Okay, shifters are a little bit expensive because I have to be able to shift by a whole bunch of bits. If the exponent was like 16, I got to shift by 16. If the exponent difference was 12, I got to shift by 12. So I basically need a pretty flexible shifter. That's actually a bunch of multiplexing. Once I add these, I actually have to round off. After I've rounded off, it's possible that I have like some leading zeros. Maybe these two numbers had opposite signs. So when I added them together, I got a lot of cancellation. I put a 1 in front of both of them, because that's the floating point format, but those 1s canceled out. And maybe not just the first one, maybe a whole bunch of bits are 0. So I have to have a piece of hardware that checks how many leading zeros I have, and another shifter, right? A shifter that now takes the mantissa and shifts it until I get a leading 1. Because that's implicit in the format. I have to have a 1 that starts this thing. Okay, that's another pretty expensive shifter. I have to remember how much I shifted by, and I actually have to adjust my exponent. Okay, so there's another adjustment of my exponent. I figure out what my sign is. That's pretty easy. And then I pack the output back into this sign exponent mantissa format, and I'm done. Or at least I might be done. Okay, so in FPGAs, if you're doing floating point hardware, you can write it all from scratch. But also you'll find in Quartus that has like IP functions that would do floating point hardware for you, because this is kind of a pain to do, right? There's a lot more work to write than what I've given you in assignment 1. So you would probably use these IP cores that do things like floating point add and so on. And you'll see that those have an option of, do you actually want to be IEEE compliant or not? Because the IEEE floating point formats also define what happens if you divide by 0, you get not a number. If you multiply two things that have become too big to represent, you get an infinity or a negative infinity. So they have a bunch of special values that they have to check for and encode. So there's some additional logic that goes on. Usually in something that you're trying to make quite efficient, you're like, I don't care, right? Like you kind of care, but you're like, I am building hardware. I will do the extra work to make sure that doesn't happen. So you often do not generate the hardware for that, right? You can in these IP functions, but it's going to make your hardware bigger. So if you put all that in, your hardware is even more expensive, but you can cheat and say, I just won't do that. And now I'm kind of in between IEEE floating point and fixed point, because you don't do everything that IEEE floating point would do. Does that make sense? How many people want to do the assignment 1 in floating point instead? Right? So it looks so easy. Actually, if anybody does want to do it in floating point, go ahead. I'll give you a bonus mark. But it'd be a lot harder. Yeah.
So you actually need to check if any of either of the two numbers is 0, because 0 is also a special case.
Yes, you're right. So I did actually, the 0 has a special encoding. So I'd have to think carefully about if I ignore that, will I actually get the right value for this addition? So yeah, there's like extra special values and stuff in there too. So it is more complicated. Okay, any questions about the assignment 1 that I have not actually released, but I'll give you some background on? Yeah.
You mentioned that we're going to be comparing the efficiency of different approaches.
Yeah.
So are we doing this on an FPGA, or are we just
You're basically running a test bench to figure out how many cycles, and you're looking at the static timing analysis report to see how fast it runs. Okay, so you're compiling it through both Quartus and simulating it. We don't put it on a board because partly it's a pain for me to go set up 30 boards and maintain them, but also that's not how people check performance for FPGA applications. Like what the static timing analyzer tells you is how fast you can run your design. No one, frankly, cares very much if you put it on a board and you say I ran it 30% faster. They're like, you can't do that, right? That doesn't mean it's going to run 30% faster on every board. So you've kind of put it in system for final testing in system, but this basically the performance of something like this you get from simulation and static timing analysis. Does that make sense? Yeah.
And you write both in Verilog and system Verilog?
You can mix system Verilog and Verilog, yeah. I mean, basically system Verilog in many ways is like a misnomer. Like there's like a Verilog 2005 standard. I think there was a Verilog 98 standard before that. System Verilog probably should have been like the Verilog, whatever, 2013 standard. I think basically for marketing reasons, they said, no, we're going to call it System Verilog. But you can basically just think of it as it's the latest generation of Verilog.
Like C++ but for Verilog.
What's that?
Like C++ but for Verilog.
Yeah, I guess that's a good way to think of it. So, okay, so now I'm going to stop looking at the projector. We're going to go onto the chalkboard. So in lecture, this is a concept map of like how do the things that we're talking about in this course relate, because we are kind of jumping around a little bit. So in lecture 1, we're talking about, well, what are FPGAs, some economics, why would we use them? In this lecture and the next lecture, I'm going to talk about compute models and how we can use them to organize hardware, right? Like think about what we might put into an FPGA or frankly an ASIC, right? You could use the same kind of thinking of deciding how I might organize an ASIC. Okay, so with that, I'm going to turn this off. Let's see. Okay, so the textbook, the reconfigurable computing book, makes this distinction of compute models, which is kind of how you think about the computation, and system architectures, which is how you organize your hardware. I'm going to kind of blend them together a little bit, because I kind of find you think about how you organize your computation, it usually leads you towards how would you make the hardware pretty clearly, but it draws more of a distinction. Okay, so that's basically this reconfig computing book, and it's chapter 5. So that's the reading for this week. So let's see, we could use a very general compute model. So let's talk about a really general one. Okay, so a really general compute model, one example of that is CSP, which stands for Communicating Sequential Processes. Has anybody heard of this? How many people have heard of that? Okay, finally, I've got something people haven't heard of, so that's good. Okay, what does it look like? It's basically a sequential process. Okay, so a bunch of instructions, a bunch of steps that are going to execute in this blob, but I don't have just one. I can have another sequential process here, another sequential process here, and they're communicating with events. So this one can send an event to this. This one can send an event here. They can send events back and forth to each other. Okay, so this, what does this actually remind you of? Like, sorry, go ahead. Yeah, it is a lot like an FSM. Yeah, you can think of it as parallel programming. Like you have a bunch of tasks and they're communicating through semaphores. One of you guys?
It's like a PC, but you have like a CPU and a GPU.
Yeah, it could describe the CPU and the GPU communicating as well. Yeah, Alex?
Reminds me a lot of a video game. Like you're doing like a game engine. So like an event will occur and then you want to respond.
Yeah, so a lot of parallel software is written this way, right? You have things that handle events and they get woken up and they run through a bunch of instructions. Sorry?
Like sockets.
Sockets, yeah. So we've seen this a lot. There's actually one thing that this reminds me, this is basically Verilog. If you actually think about what is the standard of Verilog or VHDL, they are written of, you can write processes. You literally have like in Verilog, you have like these always blocks, and in VHDL, you have processes. And that's what they are. They execute sequentially, and then you have signals that go between them that actually are communicating. So this is why Verilog can describe so much stuff, because its fundamental organization really is this, right? But as people have said, it's not unique to Verilog. This is a way that we can organize a lot of computation. Okay, so it's really powerful. Because we can describe a ton of things this way. You can write, for example, a lot of different Verilog, but it all fits into this basic structure, right, of sequential processes that are communicating. So maybe we're done, right? So we've got this communicating sequential processes. You can pretty much describe anything in it. So maybe this is like a super short lecture, and we're done. And I see some people are got a few thumbs ups, actually. So, okay, so I'm sorry about that. Now you're going to be disappointed, because there's going to be a reason why we're not going to stop anyway. So it is really powerful, but the problem with it is, or the limitation is, it doesn't give us much guidance. So we could stop here and say that pretty much describes pretty much all forms of hardware and software that we can think of. But it's so flexible that it doesn't give us much guidance to think about how we might organize a computation. Or reasoning about them. So it doesn't give us much guidance in reasoning about a system or implementing a system. So we're going to basically take this. This is like the kind of most fundamental compute model, but we're going to come up with ones that are much more restrictive. They don't describe as much of the computation space, but they give us a lot more insight of how you might implement this in hardware or how you might implement it in software. So they're very useful in organizing your thoughts. And that's the whole reason they exist. Okay, so people didn't know what this was, so you probably don't know who invented this, right? So this was Sir Tony Hoare, invented communicating sequential processes. He won the Turing Award for it, so it was very well received. Anybody else know what Tony, have you ever heard this name before? Do you know anything else that Tony Hoare did? Yeah. Yeah, he also did quicksort. So I think one year somebody guessed he was on The Sopranos. No, he wasn't on The Sopranos, right? So yeah, he had it's pretty impressive. Okay, you win the Turing Award for this. You also come up with the fastest known sorting algorithm. So difficult act to follow. It's the only thing I was going to say there. So, okay, so what we're going to do though is I'm going to go through more restrictive systems. And my rule of thumb is that it's a good idea to use the most restrictive system that kind of can capture the hardware you're trying to build. It gives you the most guidance and usually results in the most efficient hardware, right? Because you get rid of all sorts of extra control that you don't need. Okay, so more restrictive is going to, yeah, so basically it's going to help us with reasoning and efficiency. Okay, so the first compute model I want to talk about is one that is really good for hardware, very good for FPGAs in particular, but also good for ASICs. We talked about it in the first lecture. It's streaming data flow. And there are actually a few variations on this one. Okay, so it maps really well to spatial hardware. Again, we talked about it. It's basically I've got a stream of data coming in. It goes through some operators that we can implement in hardware. So maybe and I can cascade those. So I can compose bigger systems by having additional operators processing the stream. And we saw that we could also make it faster by doing things like pipelining. Okay, so we could put a pipeline register there, and this would work faster. Okay, so there are a bunch of different variations of streaming data flow. So the simplest one is called single rate synchronous data flow. Okay, and that's basically the one we went over last week. Okay, so our operators are always the same. Okay, so it's F and G never change, always doing the same thing. And data flows through all of the operators at the same rate. So it's like one clock frequency. We send in, 1 million pieces of data per second. 1 million pieces of data come out of F. 1 million pieces of data per second come out of G. And 1 million pieces of data go outside. So everything's running in lockstep. Okay, so data flows through all the operators at the same rate. Okay, so it's very, very efficient in FPGAs. And it's very pipelining friendly. Okay, so let me draw what one of these operators might look like in hardware. Because we talked about pipelining last week, but I want to go through a few rules. Like basically, this is very pipelining friendly, so it's a good point to kind of pause and say, well, how do we do pipelining in a kind of rigorous, sort of mechanical way to try to get more performance out of this kind of stuff? Okay, so we've got this operator F. And let's look at what that might look like. Let's say it has some sub pieces of hardware in it. Okay, so this F operator, if I look inside of it, it's got these sub-operators in it. So I've expanded this a bit by looking at the graph of how these sub-operators are connected together. So where can I pipeline this? Right, so FPGAs really love pipelining because they have lots of registers. You're going to see this when we get into the architecture. There are kind of registers everywhere. So pipelining is pretty cheap. Also, FPGAs have a lot of delay in the wiring. So it limits their clock speeds, but pipelining helps counteract that. So there's kind of a big gain to pipelining and not as much cost as there is in some other technologies. So it's always a good optimization, but it's particularly useful in FPGAs. So I've got this thing. And for us to be proper streaming hardware, I've got, say, a register out here and out here. Okay, so, but that's all I've got right now. And I don't really know what this does. And that's one of the nice things about pipelining is you can actually pipeline spatial hardware without really knowing very much about what it does. So my teammate did this, or maybe my TA did this. I don't really understand what's inside these hardware blocks, but I'm still going to go pipeline them. So where can I pipeline this? Yeah.
Well, the longest path is through F1, F2, F3, F4, so I know I need at least that many registers.
Okay, so you want to cut this. You're kind of saying, so you're kind of going to like, this is a desirability thing of the longest path is we're going to limit my clock frequency. So saying, I do not like that path, right? Because that's the longest one. Yeah, okay, so you want to pipeline that.
So I need at least a register along each of the arrows on that path.
Okay, so you're saying go all the way to put a register on each one. So go there, go there, go there. Okay, so you put registers on all those.
Now F1 can go directly to F3, but there's sort of two registers
Okay. See, what do you want?
So 2 registers between F1 and F3 along this area.
So what are you doing now? So tell you, I think it's sounding good, but why are you doing that? So this was limiting my clock frequency. I put 3 registers on it. I didn't even just put 1, I put 3. My clock frequency is better. I'm done.
Any path I take from the input to the output to me needs to have the same amount of registers to keep.
Right. So if my circuit was working before, and it was, right, the TA was really good, works perfectly, right? Then to pipeline it, I need to keep exactly what you said. If I'm going to add latency to some paths, I must add the same latency to all paths that go between inputs and outputs. So you're saying this path, you've added 3 cycles of latency, and this path, you've added 1. And that troubles you, I think. Is that correct? Should trouble you because it's not going to work, right? So, and this path, you've added 1 as well. So yeah, it's not looking good because the output here would be a function of some intermediate data that's from 3 cycles ago, like 3 inputs ago, and some data that's from 1 input ago. And that's kind of madness, right? If this is computing banking records, it's now like arbitrarily shoved together information between you and your neighbors 2 doors down. Maybe undesirable. So,
It just mixed me with Jeff Bezos and I'm happy.
so, okay, so what do you want to do to fix this?
So 2 registers in the direct path between F1 and F3.
Okay, so you're saying put 2 registers here. Okay, so 1 register here, 1 register here. So now you've got 3 registers through that path, right?
And then 2 registers in the direct path between F2 and F4.
2 registers here. And now you've got 3 through that, 3 through that, 3 through that. Looks pretty good. So what do people think? Everybody with you? Yeah, so I think this is good. So yeah, you have to latency match. So you have to latency match all the input to output paths. So I'm going to show you a trick that actually helps you with this. So this is called a feed-forward design. Okay, there are no loops basically. So the data just flows from inputs through a bunch of processing and moves towards the output. So in a design like that, what I can do is I can find legal points to pipeline. And maybe I'll do this again. Well, maybe I don't have to do it again. If you find a cut, all right, in this circuit that disconnects your inputs from your outputs, and it's a directed cut, like all the edges going across the cut have to be going one way, then if you put a pipeline register on every one of the edges you just cut, it will be legal, okay? So let's try it. So if I put, I'm going to erase this and we're going to try it a few times. So this is the fundamental constraint, balance the latency of all the paths. So you can just directly go and do that. In a complicated circuit, sometimes it can be a bit harder to see, am I balancing the latency or not? So this cut technique can be a useful way to rapidly find legal pipelining solutions for a design that doesn't have loops like this. Okay, so let me just draw this again so I can basically play around with it. So I've got F1 going to F2, going to F3. I've got this path in between them, and they both go to F4. Okay, so if I look for a directed cut, okay, so it's a directed cut, so I've got to pay attention to the direction the arrows are going across my, my cut line that divides the inputs from the outputs. Okay, and it adds the same latency to all paths. Like the same latency is really the fundamental constraint. But let's look at that. So could I do this? So there's a cut. Does it disconnect my inputs from my outputs? Yes. Okay, I got one input, one output, I can't get past it. Are all the arrows kind of going from my input side to my output side across the cut? So they're all going in the same direction. So yeah, this is legal. And this would imply this pipelining. Put a pipeline register there, put a pipeline register there. And if you go and walk through the latency analysis, you'll see I have added the same number of cycles to everything. Like no matter what path I take through this, I have one extra cycle of latency. So it does actually pass my latency balancing. What about this one? Can I do this cut? Okay, it also disconnects my inputs from my outputs. All the edges are going in the same direction from the input side to the output side, so it's fine. So I could put these registers in too. And I can stack these. You know, I can do both of these. So I can do that cut, then I can decide to do this cut as well. What about this? Could I do a cut like this? Okay, so this cut goes like diagonally there. Is that a legal cut? Okay, so it does disconnect my inputs from my outputs, and all my edges are going the same way, right? From the input side to the output side. So I can do that. I can put these registers in too. And I think actually at this point, I actually rediscovered your pipelining solution because you just kind of jumped right to, I'm just going to pipeline everything, and you did it correctly. So good job. Yeah.
Do you need to disconnect all the inputs from the outputs?
Yeah. If I had a bunch of inputs, I guess it depends if you have, like if your sub-circuits are totally distinct, right? Like for example, if I made another streaming thing here that's just completely different inputs, completely different outputs. Okay, well those things have like, they have no relationship to each other if you know that the outputs are also going to kind of different destinations and so on. Does that make sense? Like you know that the outputs outside are not assumed to be in any kind of alignment. If they were assumed to be in an alignment, then you actually have to treat all inputs and outputs. If I had another input here, you know, that was going in there, I do have to take that one into consideration because it's like part of my whole circuit. It's clearly coupled together.
By input, you mean
So maybe this is like two inputs coming into this, right? Instead of one input, I've got two inputs coming in. These two inputs must be, you know, synchronized. So there are registers here on both of them. If I had this additional input coming in, I have to consider it as I'm cutting things. Does that make sense? So yeah, for simplicity, I just drew one input. But this could be a bus. There could be a whole bunch of inputs. I got to cut them all. And I could have a whole bunch of outputs, same thing.
So the inputs here are basically the output of the last stage clock that you encounter, like F1 here, because it comes from a clock. That's considered an input? Is that how?
Yeah, an input is like, it's not part of this compute module, right? It came from the outside this compute module and went into it. So this could be the edge of my chip, but more commonly, it's actually just the edge of some module that I'm talking about, right? Like some operator that I put a box around. Yeah.
So I guess in this case, we know, okay, we kind of knew already which cuts to take.
How could you do this algorithmically? That's a good question. Let me think about that for a second. Before doing that, I want to show that, so far I've shown you all cuts that actually work, okay? So what if I did, what if I did this cut? Okay? So this cut goes diagonally through here. Is it okay or not okay? Yeah, this one's not okay because while it does cut an edge between inputs and outputs, like the input is disconnected from the output, it has no directionality, right? Like this one is going from this side, the input side, to the output. This one's going from the output back to the input. And this one's going from the input to the output again. So I haven't made like a directed cut. Like the edges are going across the two partitions in different directions. So I can't do this one. That wouldn't make sense. I also couldn't take something that's not a cut. I couldn't just say, well, could I just put a pipeline register only on that edge? Well, it's not a cut. I didn't disconnect my input from my output, so it's not allowed. Because basically it's not going to maintain the latency property. So the latency property is the really fundamental thing you have to follow. This directed cut technique is just a shortcut. For circuits like this, which are pretty common, where you have no loops, you can apply this cut technique. Yeah.
So sort of going back, is a cut then anything which causes sort of a bipartition?
Yeah, the definition of a cut is it chops a graph into two pieces. And we want to cut So we need a cut. We have to remove edges. We have to identify a set of edges that will cut the graph into two pieces. And then we want one of those pieces to have all the inputs, one of those pieces to have all the outputs, okay? And all the edges that we cut, we want to go in the same direction from the part that has the, all the inputs to the part that has all the outputs. We don't want any going backwards. Does that make sense? And yeah, I find when you have a bunch of hardware, this can be, you just draw it out and you can start doing these cuts. It can be easier than to sort of start calculating through all the paths that I match the latency. But you can do that if you find that easy too. Usually this one you can pretty much do graphically. Like you just make a little schematic of your design and you start drawing cut lines on it and saying, okay, I can put pipeline registers here, there, and everywhere. Okay. Whoops. So I guess we wound up twice in the same spot where we put registers kind of in a whole bunch of spots. If I didn't have this many registers, so in this case, we kind of pipelined to the max, right? Like we just put like registers pretty much everywhere we could. I mean, we could just say we'll make another cut here. We'll do it again and we'll put more registers. So I guess there is no limit. I could put even like multiple registers on these cuts by just doing it over and over again. So eventually you probably want to stop. So as we're doing these cuts, we now have a technique to find what are legal places to put pipeline registers. What do we generally want? Like if you're going to do a limited number of cuts, which ones are most desirable? What do you think? What properties do you want in these cuts? Yeah.
There should be balance on both sides of the cuts.
Yeah, so what we'd like is cuts that are balanced. Okay, so we prefer ones that are balanced. They have roughly the same amount of logic on both sides or the same amount of delay on both sides. Why? So it makes sense, but why do we want that? Yeah.
Because you want to minimize the maximum layers.
Yeah, you want to minimize the critical path, like the longest path between registers. So if I put registers kind of in the middle of my existing paths, it will tend to achieve that, right? It's going to guide me more quickly towards that. There's something else you might want in your cuts. Okay, so anything else that you might consider in your cuts? Yeah.
So on the critical path, right, you want one cut through each segment on the critical path?
Yeah, so I guess you're basically, yeah, so you do want to cut the critical path, maybe a lot of times. Although what tends to happen is after you cut the critical path, something else becomes critical, which is okay, then you go cut it too. But that as you kind of pipeline deeper, what usually happens is you need to pipeline, you get more and more critical paths, which you can still attack. But basically, your first pipelining, you might go, there's like an obvious path, I've got to make sure I cut it. And next, you might say, now there's a bunch of paths, I got to make sure I cut all of them. And then even more and even more. So, but you do want to cut, you're right, you want to cut the longest paths. So I told you that FPGAs have lots of registers, but it's not infinite. Do all these cuts cost me the same in terms of register counts? So, yeah, so they don't all cut this. Basically, they don't always cost you the same amount. So if you find a cut with few edges, okay, so if I had like some hardware where I had a bunch of stages like this of computation, and then I basically branched out and went parallel to a whole bunch of units and cruised along for a while, and then maybe produced a whole bunch of outputs. If I have, near infinite pipeline registers, I might put, pipeline everywhere, pipeline every single one of these things. But if I've got some limits on how many pipeline registers I can use, so in FPGAs you can use a lot, so probably it's not a bad strategy to say, let's just try them all. It'll cost you some area, some power, but it's still not a bad trade-off. In an ASIC, registers are actually quite a bit more expensive. I mean, it's not so much that the registers are more expensive, it's like the cost of the registers is not that much cheaper than in an FPGA, and the cost of the rest of the logic is quite a lot less. So the relative cost of putting the registers in is quite a bit more, and they're not prefabricated. You know, you're basically, the more you ask for, the more you're putting in. So in an ASIC, you will pipeline quite a bit too, but you will start hurting, right? If you pipeline really deeply, it is going to start to cost you some power and area. So maybe I don't need to cut all these. You know, I don't need to go that fast, or there's other parts of my design that can't go that fast, so it's pointless to cut them all. Given that, where should I cut? So you guys told me, well, kind of in the middle makes sense, right? Try to have around the same delay on both sides. So this is kind of in the middle. This is kind of in the middle. Where should I put my cut? What do you think? What's that? Yeah, here I'm just kind of, let's assume they're all roughly the same. You're right, you should consider the delay of each unit, because really this isn't just, you know, how much have I got on the left, how much on the right. So you'd cut it here. Yeah, and if I only needed to cut this once to meet timing, this is a logical place to cut it, because it adds one register, okay? And if I cut it here, I add 4 registers. So you would like to actually cut in spots where there are a few edges. And usually, yeah, often you won't have to pipeline to this, you know, just kind of everywhere you possibly can, because you've got other critical paths in your design that are in maybe your control logic. And it's just not going to, I'm going to talk in a minute about why that might be harder to pipeline. So once that's limiting your frequency, there may not be a purpose to pipelining all this other stuff anymore. Yeah.
So on that path that goes from 1 node to 4 nodes,
Yeah.
you can put 4 flops per registers, or you can also just put one that fans out to 4, right?
I guess that's true. You're right. You could, if so, I have to put, let me think about that. Yeah, I have to make this, I need to put a little more logic here to make you want to go here. Okay, so I put another node here. And now I can say, oh, the question is, do I cut here or cut there? But you're right. These ones, you could say, instead of putting 4 registers in, I'm going to do an optimization and say, let's put a register, kind of push it back into this thing. Does that make sense? So by using this kind of mechanical procedure where I'm just cutting edges, I would put 4 registers in, but you're saying, well, I can recognize I could kind of combine them because they're all driven by the same thing. And you're right. Let's see. Okay, so that is so that's an important optimization. And you'll use it in assignment 1. So in assignment 1, we're asking you to kind of use different compute models, and one of the things we want you to do is actually pipeline it and see if you can keep it correct and make it faster. See how fast you can make it. Okay, so the blocks of hardware that I've been showing you didn't have any loops in them. Okay, so they're like feed-forward data paths. The data flows from inputs to outputs, which is a very nice thing, but you can't do that for everything. Sometimes you have loops. Okay, so for example, control logic often has loops in it. So let's say I have something like this. So I have my stream of data coming in, got an operator, got another operator. Okay, I register that. Okay, and that produces my output. Okay, I'm putting the yi and xi here to show you it's really a stream of data. It's not one number, it's a stream in time. And this one actually has a loop. Okay, so my output feeds back and affects the next stream of data. So let's say this is not running fast enough. I want to pipeline it. Where would you put a pipeline register in this thing to make it faster? So you'd like to put a register here. Okay, so let's put a register there. This will clock faster now. Okay, because my longest path was F1 plus F2, and now that path doesn't exist. Now my longest path is, you know, either from X to this register or from Y to this register, but it's shorter. I cut F2 out. So from a timing perspective, my clock frequency looks better. Am I allowed to do this? What do you think? Yeah.
You can't, because now you're introducing one more clock cycle delay, so maybe F1, like your XI and whatever output your F1 would be one cycle now out of sync.
Yeah. Yeah, so basically this, That's exactly right. So it used to be, so let's think about it from a latency point of view. Okay, so my original y of I, if I write out this equation, it was basically take f2 of f1 of, what were the inputs to f1? The inputs to f1 were x at the current time, so the current x, and y one clock cycle before, like the old y. Okay, so I don't know what f1 and f2 were, but it doesn't really matter. Like that's my function. It's taking y from one clock cycle ago, x from right now, producing a new value. And if I write that out after I put this pipeline register in it, it's different, right? So y primed of I is basically now, it's actually computing a function f2 of f1 of x, the current x, and y of I minus 2. Okay, this is like an extra cycle of latency to produce every y. So when you walk through the equations, we're actually now computing something that is just different. Okay, and there's no actual way to fix this. Like it's broken. I can't do this pipelining. So it fails my latency test. If I do my cut test and go, well, does that disconnect my inputs to my outputs? Well, not in a directed way, right? This edge is going from input side to output side. This edge is going from output side back to input side. So it also fails my cut test. So it doesn't work, right? If I do this cut, the circuit functionality has been changed. And I can't, like, if I put a register here, is it going to fix it? Like, what do you think? Is that going to make things better? So I just drew this cut. What if I put a register here? Does that make things better? No, it doesn't fix it either. Because, again, this is not a directed cut. Like, basically, we've got a path from output to input that we've cut and a path from input to output that we've cut. If we put registers on both those things, it still doesn't actually line up our latency. In fact, this register kind of made things worse still, because now we're computing a function of x of current x and y of I minus 3. So it's not getting better. It's kind of getting worse. The more latency we insert around this loop, it's just getting worse and worse and worse. So what this means is that we kind of like this feed-forward hardware because it is so friendly to pipelining, and you want to be careful about loops. If you can avoid loops, it's good. But you can't usually avoid them in everything. For example, finite state machines, you've got some control logic. It fundamentally is usually looking at the current state to figure out what to do. So that means there are loops in it. You try to keep that logic simple so that it's reasonably fast, even if you don't pipeline it. We'll talk about there are some things you can do with this. So it's like not a complete disaster, but it's harder. If you have the option of building hardware like that or hardware like this, you probably want to build that. Okay, so let me erase this little bit here. Okay, so that was all single rate synchronous data flow. So everybody's working on the same clock. All my data's flow. Everybody's producing the same amount of data, right? One unit of data goes in, one unit of data comes out. Not everything can do that. So okay, so what we just looked at was a special case of a data flow architecture. It was synchronous, meaning it was all one clock, and it was single rate, meaning everybody was producing the same amount of data. So we can go to a slightly more general compute model called synchronous data flow. Okay, so what does that mean? We're removing the assumption that everybody's producing the same amount of data. And that can describe some additional computations. Okay, so what's the problem? So what if some of our operations produce more output than input? Okay, so an example, this might be hard to do. Let's see, anybody, can you think of an example of that? Yeah.
Just gonna ask, does that also apply for more inputs than there are outputs?
Yeah, that's also a problem, right? So the single rate basically is everybody's kind of in lockstep, not just in clock frequency, but also everybody's super happy. They all produce exactly the same amount of data all the time. It's like a bucket brigade, right? Any ideas of what would be an example of this? I have like my favorite ones. Yeah, what do you think?
I guess if you have like a divide or add or multiply unit in hardware, use different units won't necessarily take the same amount of clock cycles.
Clock cycles is okay because I can pipeline it. Like as long as the rate, well, okay, I guess that's a good point. If you didn't make it single cycle throughput, you're saying it might take you a bunch of clock cycles so that it can't, there are many clocks where it can't actually produce anything. Yeah, you're right. That's a good example. So you've got like a divider that's kind of an iterative algorithm. So maybe it takes 30 cycles and then produces an output. And it's hooked up to like adders that can produce data every single cycle. Yeah, they're out of step. You could basically slow everybody down by a factor of 30, but that's kind of what you'd have to do if you want to stick with single rate synchronous data flow. Otherwise, you have to say, let's make our data flow, let's make our compute model more general. So yeah, so one of the ones that I think of here, because I've seen lots of signal processing designs, because again, they're pretty dominant in FPGAs, they're very common in FPGAs. So an interpolation filter. Okay, so there's lots and lots of examples, but one would be, again, think of like a cell phone base station. You got all these antennas sending in data. It's all digitized signals of what's coming off of the antennas. And often in the signal processing pipelines, you may go, I need more resolution at this point of the algorithm, and you'll actually use an interpolation filter. So that means you have data at 100 million samples a second, and you actually just fill in all the gaps to make it 200 million samples per second. So you fundamentally have at a certain point in your pipeline, 100 million pieces of data per second are going through, and the output of this interpolation filter is, its goal is to give you 200 million per second with all the gaps filled in halfway in between to give you essentially more resolution for the next stage. It's fundamentally different than the 100 million that came in. It's this whole purpose. And you also get the exact opposite. Again, in signal processing, you have a decimation filter. So all that means is I've got a stream of data, and at a certain point, you go, I don't need to be quite so accurate. I'm past that part of my algorithm. I'm going to drop every second sample. Okay? And now my data rate goes down by a factor of 2. So both those things kind of fundamentally change the rate. And it's pretty common, again, in complicated signal processing algorithms that you have these rate conversions happening multiple times in a processing pipeline. But this basically means we can't run everything at the same rate. Okay, so what could we do? So we got this streaming hardware, and it's very efficient, but it's kind of fragile. Like every single clock, everybody's got to have a next piece of data, and it moves on to the next stage. And now we're saying sometimes we might not have a next piece of data. So what would you do?
I guess handshaking or some version of clock enabler.
Yeah, so you've got to do something like that. So it's the right idea. Yeah.
Multiple clock domains.
You could use multiple clock domains, and that is done sometimes. You could say, okay, this is exactly twice as much as that, so let's run it twice as fast. Or you could use clock enables to say, let's enable you every second cycle. You can do that. It solves some problems, but you have to have these kind of nice multiples, and it has to be very deterministic. Your example of a divider, if I made a divider, and dividers, to make the most efficient dividers, some numbers are easier to divide than others. They sometimes actually finish early. And if I start doing that, it can get quite hard to balance by just saying, run this at a different clock than that.
But if you have like a handshaking signal that sort of says the data that I'm outputting is valid for this instance.
Yeah, so the handshaking one is actually a very general approach. So you're saying do a handshake, and you actually said one of the words that I was hoping to write down. So you said, so we're going to kind of build up to this in a couple steps. But the first way to make sure you can handle different rates of data is we need a data valid signal. Okay, so the reason this is so fragile, but so efficient too, so if you can use this, it's really efficient, is there's no way to say that I don't have valid data. right? It's just everybody's got to have valid data every single clock cycle. There's no way to encode, this is not actual valid data. I'm just working. So once we have some things running at different frequencies, we can put a data valid bit. We don't have to put a data valid bit on every bit of data. We put it on every kind of unit of data. So if I'm producing a 16-bit number, I can have one data valid bit that says, should you pay any attention to this number or not? If I'm producing a whole vector of numbers, and I always produce that as a unit, I could have a data valid bit for the whole vector, saying, should you pay attention to this vector, this clock cycle, or should you assume that there's just nothing here, right? Okay, so basically on all of my data here, so this is like some amount of data, maybe a 16-bit number, maybe it's 512 bits of like data because it's a whole vector. I not only send the data, I send a 1-bit signal along that says whether it's valid or not. And I do that here too. And this also does it. Okay, so the cost isn't too high, right? I add like valid bits on top of, but only one per essentially operand. And I add a little bit of logic that says, well, my output data is only valid if both my inputs are valid, right? That's our equation. Yeah.
But I guess you also need to manage back pressure because if something's already received data, you can't sort of.
You're right. So you're one step ahead. We're about to go into another compute model that like basically goes further because valid it makes the compute model a little more powerful. It does actually solve it for some systems, but in most you need to add more. You're right. So hold that thought. The other nice thing about this is like I can still basically pipeline the same way I did before. So if I look at this and I say it's not fast enough, I can say, well, here's a cut, separates my inputs from my outputs, and I'm going to pipeline it. And I pipeline my data and my valid exactly the same way, right? These signals are flowing beside each other. They're in the same edge. If I pipeline the data, I pipeline the valid. Pipeline this data, pipeline that valid. So I found this cut, I just do it. That actually helps you. Your control logic is kind of local. This G produces whatever data it's supposed to produce, and its data valid is just the end of the two inputs. And if I want to start pipelining, I just treat this whole thing as like a unified piece of data, unified data bus. So I've had students in prior years say, well, maybe you can make some control logic that says like every third cycle, this one's valid and so on, and then every 7th cycle, this one is valid, and if this one's doing something, then mark that as invalid. So they try to come up with some kind of centralized control scheme. And in theory, you could do that, but in practice, it's really hard to write. So the nice thing about just tagging your data with valid bits is your control was a form of data flow control. It's kind of distributed, it's kind of mechanical, right? You apply certain rules and it just works. Let's see. Okay, so basically here, G executes when both inputs are valid. But you've already kind of flagged a problem here. Like we still need to make sure that G can always keep up with, like basically this is still kind of limited. Things could go wrong if F1 and F2 don't produce valid data at the same time, and if G ever like kind of couldn't keep up. So we kind of fixed some of our problems, but this can only still be used under fairly tight conditions. Yeah.
G doesn't need to validate the data, right? It can just echo it and like just pass the valid signal to G. Because whatever you do, there is a bubble in the pipeline. That's unavoidable.
Basically, the idea is it needs to put a valid on its data because some downstream thing might be looking for a valid bit too, right? And if F1 and F2 didn't have valid data some cycle, G is going to produce some garbage, can produce anything it wants. There's no valid data for it to process. But it should produce like that it's valid as 0. Okay, so it can put any garbage it wants on its output bus as long as it marks it as 0 or not valid. So if either one of these is not valid, it really can't compute, and it has to say I don't have valid data. Okay, but basically we still have some pretty tough limitations on basically the speeds of F1, F2, and G so that no data is dropped. So in particular, like G has no way to tell F1 or F2 to wait. So basically it always has to be, if they send it data, it has to be able to keep up. Okay, it's not possible that it is the bottleneck. It's okay for F1 to be a bottleneck, but we actually kind of have a problem tier 2 if we can't tell F2 to stop computing if G is going to stop computing because it's waiting for F1. So I guess even in the case I have here, F1 and F2 have to kind of operate in lockstep, and G always has to be able to consume anything that they send it. Okay, so we've made things a bit better, but we still could have a lot of stuff go wrong. Yeah.
Would we still need the kind of like wait signal back to F1 and F2 if G operates at the same speed or faster than both F1 and F2?
Would you need any back pressure? So I guess okay, let's get rid of this one, okay? Because this one, let's get rid of this one. Let's just say I have this, okay? So I just have F1. If G can always keep up, then valid is enough. Okay, because if F1 doesn't have valid data, then G says I don't have valid data. And this happens to be, I don't know, some simple unit, right? Maybe it's an adder or something, or it can always execute at least as fast as F1. Then this is fine, okay? The case that I was showing you with F2 is a bit problematic, frankly, so maybe I should change my case. The reason it's a bit problematic is if F1 has valid data and F2 doesn't, so G will not compute. Okay, which is okay, but the problem is if F1 basically just goes on and throws away that data and produces its next piece of data, we have a problem. Okay, so in this model, G has no way to tell F1 to stop. So maybe my better example would actually be that, because it's more realistic. I've just got this producing data, doesn't always have valid data. G's got to pass it through, so it'll work. We've made the compute model a bit more flexible. But we're kind of only halfway there, right? And you want to go there. You want to go to the more flexible one, so we're going there now. So, I think I forgot to give these numbers. Okay, so this is like, we started off with just single rate synchronous data flow, okay, which is a pretty powerful compute model where you know that there's essentially no bubbles. Like you've always got data, everybody's running at the same speed. Then we went to this kind of half step, and now the next data flow model that reconfigurable computing book talks about is dynamic streaming data flow. Okay, so this basically has multiple names. Another one is elastic circuits. Okay, so the very first program model I showed you where you have streaming hardware and you can pipeline it, that's sometimes called an inelastic pipeline, as opposed to this compute model, which is called an elastic pipeline or an elastic circuit. Okay, so what is this doing? Okay, so this basically fixes all of our problems with like data rates, whereas the half step I showed you here kind of only fixed some of them, right? This fixes everything. So, and this basically is if we can think of a lot of cases where it's hard to say how much data is produced in a given unit of time. Okay, so what if some operator has a time varying amount of output? So what if the time to produce some output data varies. Okay, and I can think of lots of examples of that. Can you think of any examples where some compute module might take longer to produce its output, sometimes versus others? Yeah.
Like fractal generators, sometimes you'll have like more iterations.
Sure. So fractal generator, and I think the fundamental reason that you just gave is iterative. So if I've got an iterative algorithm, that has some convergence criteria. So fractals is one. There are ones to solve equations like Newton-Raphson iteration and so on. They usually have some convergence criteria. You don't know exactly how long it'll take. It might converge quickly, it might converge slowly. So that makes it, you can't really bound exactly how long it's going to take. So that's a problem for the compute models that we've just talked about. And any other ideas? What else might make time vary? So this is kind of like the algorithm varies. It's an iterative algorithm. We don't quite know how long it'll take. Anything else that's going to be hard to say how long it'll take? Yeah.
Something that require like a user input.
Yeah, so if there's any user input, that's a problem. And it doesn't even have to be like a user, but it's basically like outside chip, for example. Yeah, let's say I take DDR. So there's not many systems. Well, actually a lot of on-chip modules will just work with on-chip memory. So I guess I shouldn't say there aren't many things that don't talk to external memory, but it's common that at some point somebody's talking to external memory or talking to a network or something. So if you're talking to a network, it's like a user. You don't quite know when the data is coming in. If you're talking to DDR, DDR is fundamentally it's not perfectly deterministic, okay? The reason it's not perfectly deterministic is you've got to refresh it. So even if there's other reasons why it's actually got some variability in its timing that are more subtle, but a very fundamental one would be that DDR once in a while needs to actually refresh itself or it loses its state because its states just store like capacitors that are losing charge. So once in a while your read that usually takes 70 nanoseconds actually takes 10 times that, okay? So if your algorithm did a read from DDR somewhere in it, once in a while it's a lot slower. So those are reasons why your time to do something might vary. The other thing that might happen is what if the data varies, the amount of data varies? Okay, so maybe it took me longer to produce the data. Let me see if I can turn this off. Let's see. Okay, so I have my favorite algorithms for this. So can you think of an algorithm where the amount of output data might vary depending on what inputs it got? Yeah.
I guess this is a weird example of like a computer-generated proof. The amount of proof that I guess.
A computer-generated proof, you're saying?
Gave them?
Yeah, that makes sense. Okay, so you might have a long proof, you might have a short proof. I have like another one that's in the same vein maybe, but simpler, is Huffman encoding. Okay, so you think of, this is a pretty common component in a lot of systems nowadays. Huffman encoding, how many people remember what a Huffman encoding is? Anybody remember that? Okay, Huffman encoding is just entropy coding. Basically, you take the most common symbols or words or whatever in your data and you give them short bit codes. Okay, so that means if I give you like a bunch of data that is like very common signals, this is exactly what you expected to see, you'll compress it a lot, right? Because you've got short bit codes for it. I give you some unexpected data, lots of weird names in it or weird values, you get long codes and you get much more data. Okay, so this is not even the time to send something is different, it's like you have to send more data. So it's going to occupy the bus for longer. So, and it's kind of fundamental. This is how Huffman encoding works. It takes a fixed size input and it produces an on average smaller but variable size output. And it's at the heart of a lot of compression algorithms. Okay, so this is going to be a problem with the streaming hardware we built so far because we kind of have to worst case everything. Right now we have no way to say I'm not ready, which means that we kind of have to worst case everything. We'd have to make sure that we slow down the whole pipeline to the point where we can guarantee that never happens. Like everybody's always ready. But that worst casing might be really bad. So we don't want to do that. So what we want to do is instead do exactly what you've been advising me to do. Okay, so we're going to add some handshaking logic. We're going to convert pipeline registers to FIFOs. Okay, so the first thing we do is we convert pipeline registers to FIFOs. Okay, and that's so we can decouple our operators. Okay, so if you had a FIFO, so it's a buffer, right? Instead of just one stage of pipeline registers, we've got like a bunch of registers that we can bypass some of them, or usually you actually do it with memory. So you basically have a memory, you can store a certain number of values. So now if I've got a lot of data and the downstream logic's not quite ready for it, it goes into these FIFOs, and they're just going to buffer up the data, and it'll get consumed later. So that's going to help kind of handle some imbalance in the computation. But I can't make my buffers infinitely big. So, what if I keep producing lots of data for a long time and this downstream module is struggling to keep up for a long time? Like, I don't know how big I should make my buffer. In the end, I might have to make it infinite, and that's not good. So I can't make it infinite. So generally, we can't bound the communication imbalance. So FIFOs aren't going to be enough. So what do we do? You've actually already told me. So
I guess you can sort of send back a stall signal to let that.
right. So we need a back pressure or a stall signal. Okay, and we want to do both these things actually. Okay, the reason we want to have both is the buffer lets us kind of keep producing data from a module, even if the downstream module is not going to be ready to produce it. The back pressure signal is going to tell us to stop eventually before we overflow the buffer. But the buffer is going to let us kind of produce some data while the stop signal is still being generated. Okay, so this back pressure signal, usually a module doesn't quite, it takes some time for this back pressure signal to be generated and for it to be sent back to the previous module. So during that time, we want to have some buffer space where our output is not being lost. Okay, so you really want to combine these two things. Okay, so we want to assert this back pressure signal in time to prevent buffer overflow. Okay, so let me draw what this looks like. Okay, so instead of just putting pipeline registers in between, or just connecting them with wires, or just putting pipeline registers between F and G, I put FIFOs in between them, so little buffers, or maybe big buffers. I mean, that's up to you to decide, like, how many pieces of data can these FIFOs store before they overflow. And as I said, this isn't enough. If F1 kept producing data for a long time, and G was taking a long time, it wasn't producing much, eventually it would overflow this buffer, okay? And you can say, well, make it twice as big. And then I'll say, I'll run it twice as long. and I'll always win, right? You'll never be able to make it big enough. So what we do is we have this FIFO generates a back pressure signal. And when this gets that back pressure signal, it stops producing data. So it stalls it. And this back pressure signal is, you don't wait until the buffer's full, because if the buffer was full and then you produce the back pressure signal, by the time this gets it and processes it, it's probably produced at least one more piece of data. There's nowhere for that data to go. The FIFO's already full, so it's thrown away, which basically means your system is broken, like you just lost data. So this has to be almost full. And what is the definition of almost full? Well, it's basically how many cycles, if I put pipeline registers on this, maybe this has to go a long way. And inside here, maybe I put a pipeline register when I receive it to decide I'm going to stall and so on. Well, then I better check this when I've still got 3 pieces of data. So this almost full in the case I've shown you here would be I have 3 more words of data, because it will take 2 cycles for this to receive my stall signal. So it's going to produce 2 or 3 more pieces of data. So I want to leave that much space. Does that make sense? If I didn't have these registers here, then I could probably check, I could stall just when I have 1 piece of data left. Anyway, each of these things has to have that. So this gets a back pressure signal. This gets a back pressure signal. We still need valid. So this is data and valid, because there's another reason now that I might not have valid data. You might have stalled me. So G basically now only computes if it's not back pressured. So there's a place for its output to go, and it has valid data on both of its inputs. And when those things happen, it pulls 1 piece of data out of both those FIFOs, and it sends 1 piece of data over here. Does that make sense? Yeah.
So this solves the pressure issue for G, but it just pushes it back in the pipeline.
Yeah, it solves my correctness issue.
User input, right? Then we would ultimately still be losing user data.
I'm sorry? I don't know if I know what you mean.
So this is like putting pressure back to like before F1 or F2.
Yeah.
If the input was user like input,
Yeah.
wouldn't we lose information?
Oh, okay. So you're saying, like, what if the user is so fast? Okay, the good thing, okay, so if the user's a human, the user's, unless you've built really slow hardware, probably the user cannot keep up with it. Do you know what I mean? So basically, you need your input FIFOs to be big enough the user can't overflow them. So how fast, let's say the user is actually a human typing on a keyboard. So humans can type on a keyboard maybe, I don't know, 5 keys a second. So if you can store 5 pieces of data in an input buffer, then the rest of the pipeline has an entire second to process it, which is huge, right? Like this, so does that make sense? So you're right, when I get back to something that can't be back pressured, which could be the user, could be the network. So in a compute environment, it's often the network. Like I can't actually back pressure the thing sending data over the network. So I do need to make sure, so I put buffers on the, where the network interface comes in, okay? And then I basically have to be pretty sure that those buffers won't be overflowed. Like that my average over the time that buffer captures throughput will match what the network can provide. And that might be because I actually hooked it up to, I don't know, 100 gig Ethernet, and I designed this whole processing engine that it is going to be able to handle on average with a factor of 2 safety margin 100 gig Ethernet traffic, so I'm pretty safe. Maybe I can't actually. Maybe I hooked it up with 100 gig Ethernet cabling, but I can actually only on average do 50 gigs, and maybe therefore I have to watch out. If there's a long burst above that, I'm in trouble. So now you might actually have load balancing software in a data center that says don't do that. Do you know what I mean? Like you actually have to tell the load balancing software, I'm getting overwhelmed. And depending on how long it takes to tell the load balancing software might even have to have retries, where it basically gets told, I didn't actually do, like the last set of data you sent me, I just threw it away, right? So you're right. When you get outside of the chip or system boundary, you may not have good back pressure signals, and that's where you actually, they become a lot more expensive. So you try to give like essentially guarantees of I will for sure process this much in this amount of time. And if I can't keep up, I'll send you a signal, but it might take a long time, and there might be all sorts of retries, so it's highly undesirable. So in FPGA networking equipment, so another big market for FPGAs is like wireline processing, like the big routers that actually run the internet. So we're not talking like the stuff that's in your house, but like boxes that, Bell Canada has full of like, many millions of dollars of Cisco and Nokia Siemens networks networking equipment. And those kinds of boxes have very strict agreements of when the data comes in, it will come out, right? Like you are not going to drop packets. And it means they do have big buffers. The data processing engines are basically kind of oversized a bit, if that makes sense. Yeah.
In the case like this, why not have, let's say, F3 that can be reconfigured to be either F1 or F2 to help out with?
That's actually one of our later compute models, right? So you kind of go, well, maybe I could actually, so far all these operators are static, right? Like you kind of put them in your design, they stay there. And that matches certain applications quite well, but you're right, in some cases it can be limiting. Anyway, but you actually have an excellent point. There are points in systems where back pressure becomes really hard. Maybe it's impossible, or maybe it's so slow, like in networking, that by the time you've back pressured something through like, some higher level protocol of the internet, there's a lot of data that arrived. So now you have a decision to make of, do you say, I threw away the data, you must resend, or do you have a ton of buffering? And people use both. Or do you over-engineer it? Do you basically go like, I'm going to advertise this data processing rate, but I really built twice that to make it very unlikely that that happens. So.
At that point, that's how you're marketing your product. That's my maximum data rate, and your customer already knows you can't handle more than that. So they're only going to put it in applications that where it won't.
Yeah, if you have where it gets tricky is if your data rate does vary a fair amount. Do you know what I mean? And so if your data rate's pretty fixed, then you kind of go, look, this is the data rate, and that's what I'm going to handle, and it's pretty deterministic.
In real life, it doesn't happen because the people that use an equipment, they already know what it can handle. So.
Yeah, you have to give them a spec, yeah.
So with dynamic streaming, if I have a whole system, so I have A going to B going to C, wouldn't my whole system be bottlenecked by, I guess, like the slowest component? Like if my A is the slowest and it's early on in the system and it's streaming forward, then everything is kind of just waiting for A.
Yeah. So the reason this is often called elastic circuits or elastic pipelines is it still is a pipeline. Okay, so if I built G to be a lot slower than the stuff in front of it, it's an unbalanced pipeline. It's kind of stupid, right? Because G can't keep up with everything else. So I either underpowered G or I spent too much area on the other things. But a pipeline's always limited by its slowest component. What we've done with elastic pipelines, though, is we've gone from every single cycle, everybody must keep up with each other, to on average, they should keep up with each other. And if they don't, it's actually still correct. Like if G was always slow, it will back pressure these things. Let's say I was kind of foolish and G's only 2/3 as fast as these things. It will back pressure them on average 1 out of 3 cycles. The system will still work. Was it a super great design? I mean, if that's happening all the time, I should have really made G more beefy, or I made another copy of it or something. So in the next generation, I probably would go do that. But there also can be exceptional events, right? Like most of the time, G is balanced with F1, but once in a while it's not. And that's no longer an issue for correctness. It'll always work. Does that make sense?
Yeah.
But I have paid for it. Okay, so if you think of like before I had just wires, or if these are pretty big modules, I'd probably put pipeline registers here. So if this is maybe a 128-bit wide bus, I had 128 registers here. Now I have a FIFO with 128 bits in each word, and I have several words. I have to have pretty much at least 2. The reason I have to have at least 2 is if I don't have 2, I wind up with really bad clock frequency, because basically I need to have data come into this FIFO, it gets full. In that same clock cycle, I say you're full and you must stop. So that's basically a long path with no pipeline registers. So you don't want to do that. You want to have at least 2 entries in here so that you can have, basically, you can see the first entry is used. You say, I want you to stop because I'm worried if you send me more than 1 that it'll overflow, but it can still send you 1 more data. So at least it can still keep computing while you're sending the back pressure signal. And often you want more than, so 2 is kind of the absolute minimum, right? If you don't do 2, you're going to have terrible timing. But commonly, if there's some imbalance between these things and you put some pipeline registers in, it's more than 2. Okay, but anyway, so we've gone from like a 128-bit register, for example, to several words of 128-bit wide data and some control logic. So it does cost.
Yeah, so I guess my other question then is, if you're, let's say you're an FPGA, you're working with an FPGA, and your system, you're building like a dynamic streaming system that utilizes one of the components on the FPGA, like DDR,
Yeah.
and that inherently has a maximum clock cycle or frequency. So wouldn't your entire design kind of just be limited by, let's say you're just reading from it, by how fast you can read from DDRs?
On average, it would be. So, okay, so you would
But
normally
you have,
put,
like, control over that. That's what I'm trying to say.
oh, yeah, so if you look at a DDR interface, it always has back pressure and valid, okay? Like, so it always uses, and a buffer. So a DDR interface would always use this style of compute. The reason is you can't say how many cycles it's going to take, et cetera. So you need to put valid bits, valid tags on your data, and you need to have a back pressure signal so it can say, you've been sending me data to write or read requests, and I'm full. It won't necessarily bottleneck your system though, because those buffers have gotten you now, you get the average bandwidth of the DDR, okay? And if your system is okay with average bandwidth, like if that's enough to keep your system busy, then your system will generally not be stalled by the DDR. If you're, there are certainly many cases though where the limiting thing in your system is memory bandwidth, and in that case you will be stalled by DDR, and it's kind of fundamental. What you have to do is you have to find a way to shrink your data, store more of it on chip, buy more DDR channels, use RLDRAM, use HBM2. Do you know what I mean? You have to do something else if you're fundamentally limited by memory bandwidth. But this technique will basically get you to the average memory bandwidth. You'll be correct, and you won't be stalled just by the long latency of the memory. Does that make sense? Yeah.
We usually have caches to help with that.
Yeah, you have caches. In an FPGA, usually those caches are sort of explicitly managed. So we usually don't use caches that are kind of hardware managed. You can build anything, but usually what you do is you'll have your own scratchpad memory that you're explicitly managing. So you've kind of thought of where do you put your data. This is part of how you get your efficiency, right? Like in spatial computing, is you say, I will put the data here right by the compute model, compute modules, and I will manage it myself. If you kind of go, I don't really like to think about memory much, then like a multi-core out-of-order processor is like a great thing, because it basically is spending a huge amount of hardware to say you don't have to think about what your data is. We will just figure it all out. Okay, so the last thing I'll say here is, so these are a lot more expensive than the regular pipeline registers. And so you mix these things. Let's say inside this operator G, let's say this was some kind of dot product engine or matrix multiplication engine. Let's say it's a matrix multiplication engine. So it takes in a bunch of data from these two inputs, and it stores some of it internally, and it's multiplying two matrices. And every cycle it's getting another row and another column, say, of two different matrices, and it's continuing its multiplication. Once we get the data in, we have a bunch of work to do, like multiple cycles worth of work, but we know that that work is going to finish. And it's going to finish in a certain number of cycles. Like if I built this matrix multiplication unit to take like 150 cycles, it will always take 150 cycles once I send in these two pieces of data. So inside G, I could still use regular pipeline registers. Okay, which means it's basically using our simpler program model, the first one that we talked about, single rate synchronous data flow. So while for a whole system, it would be unusual that you could say, I can guarantee all the data is valid, everybody's in lockstep. Within individual modules, it's actually pretty common that I know once my data has arrived that I have a whole bunch of work that I can do, no chance of stalling, same clock period, et cetera. Inside here, I don't need to carry the valid data, valid signals around. I don't need back pressure. I don't need FIFOs. It's all just pipeline registers. At the very end, I put the valid bit back on, and I send it to this FIFO. Does that make sense? So you commonly mix this. Yeah, we'll take a break there. I guess this is why I say also you tend to use the simplest program model that works. Inside G, if it was a matrix multiplication unit, and I know that it can't stall once it has its inputs, it would be wasteful for me to use this kind of compute model where I'm using FIFOs and back pressure all over the place. But between these modules that essentially have more variability in how long it takes, I need it. So we kind of compose it using what we need in the right spot. Okay, So let's take a break until, how about 7:05? What do you think we're going to get going again? I'll just make a note that how many people know somebody in medicine here, like studying medicine at U of T? They seem like they must be very tough, right? Because it's like super hot in here. I don't know how they take it like every day, right? I guess they're getting them used for getting them in shape for a demanding career, because this is an incredibly hot classroom. So I think engineers like it more cool. So okay, so the elastic pipelines that we just talked about, or that more general streaming data flow, it tends to use a bunch of FIFOs, a bunch of buffers. How do you build FIFOs efficiently in an FPGA? Or anyway, how would you build a FIFO? A queue. So, but how do I build it in hardware, right? So what do I build that out of? Not going to you. Alex says, Alex, I know he's taken this course before. He's a ringer. All right, so any ideas? How would I build a FIFO? Yeah.
Shift register?
Yeah, so we could build it out of shift registers. Okay, so let's say my data was like 128 bits wide. Okay, so I have 128 bits. I add 1 bit for valid. Okay, so it's valid. Here's my data. And then I basically build a bunch of registers. Okay. Connect them together in a shift register. So this is like a 128-bit wide or 129-bit wide bus. Here's the next set of registers, so on, right? So here's my input. My input flows into the shift register. And here I've got 2 words. Now, depending on how much data is in this, right? If the FIFO only has 1 item, then my output data should come from here. If I have 2 items, then my output data, well, basically data always flows in here. And if this data is valid, I should take it out first. But if it's not valid, then I should take this data out. Okay, so that's one way to build like a FIFO. So basically I need a muxing structure. I also need, like, this will be 129 bits wide. This will be 129 bits wide. And this has to go to a mux. It's actually 129 bits of muxing. Let's draw that better. And this is what will go to my next module. Okay, it'll have my valid, it'll have my data. And I need a little bit of control logic to look at these valid bits to figure out, should I send this word or that word? And there's a few different ways to build this. The way I've just built it, the data always flows into the first thing, and what goes out is the kind of oldest valid data. So this is 2 words. Let's say it's not a big enough buffer. Like maybe I need, because my latency to send the back pressure signal back is several cycles, I might need more. So I might need 4 words or 8 words or so on. And as I do that, I get more and more inputs to these muxes, and I get more and more registers. So this can actually get pretty big pretty quickly. And I guess these are the data communication paths. Yeah, so you can do this. And it's pretty reasonable if you need like maybe 2 words, maybe even 3 words or 4 words. But if you need like 8 words and the data words are pretty big, this starts eating up a lot of registers. I told you FPGAs have a lot of registers, but like it's not infinite. The structure I just showed you here is starting to, I can start making this take thousands of registers if I have a lot of words and a pretty wide data. So we use this usually for just small FIFOs. One other thing is this, how much power do you think this takes? Yeah. Yeah, this is actually quite high power because basically every cycle the data moves down 1. So everybody's kind of changing. All this data goes here, all this data goes here, all this data goes here. Data motion is bad for power. Everybody shifting over by 1 is not great. So, okay, if your buffer's small, not great if your buffer is big. So anyway, that's option 1. That's like shift registers. It's a shift register with the ability to kind of read out different words. So you can kind of get the oldest data. Any other alternatives?
Pointers?
Yeah, so pointers plus what? So, yeah, so memory plus pointer. So we can do that. That's how you do it in software, right? It's being done in DRAM. You can do it in an FPGA too. Okay, so the FPGAs are also, they have lots of registers, but they have lots of block RAMs too. So we basically make a RAM, So you ask for it in your design, and the CAD tool will turn it into like 1 block RAM or several block RAMs, whatever. And you have basically a read pointer, and you have a write pointer. Okay, so what are those? Those are registers. So I've got a register that stores, let's see, if I needed to have 8 data words, I only need a 4-bit pointer. 1, 2, 3, 4, yeah. And for the read, and I have another one for the write. Okay, so in hardware, I will have a few registers, but they're pretty small. And basically, whenever data comes in, I write at wherever my write pointer is pointing. Okay, so right into that data. And whenever you ask for data, or every cycle when I have valid data and send it out, it comes out of wherever the read pointer is. And we have a little bit of hardware logic that basically updates them. Okay, so, and this is a circular buffer. If I ever get to the bottom, it wraps around to the other side. And if the read pointer and write pointer are getting close to each other, that's the almost full condition, right? Like that's the point where I'm pretty soon, or if it's the almost empty or the almost full condition. So that's like my back pressure condition of I guess for back pressure, your condition is that I can't accept much more data. So you can basically put logic that checks how far apart are my read and write pointer, and if they're, say, within 3 words of each other, and you know that it takes you a couple cycles to get the back pressure signal back, you would actually raise the back pressure signal. Yeah?
So, I guess with the dynamic streaming data flow, we wanted to replace the registers with FIFOs. But then, if the register is only really storing one cycle of data, I guess with the FIFO, we're just generalizing it that it can store X amount.
Yeah, so it is part of your design problem to decide how big these FIFOs should be, right? So if they're really small, you can implement them in shift registers, maybe a couple words. If they get much bigger, then you're generally better to use like memories. Also, if the words are really wide, like you got lots of data, big data words, then the shift to memory happens sooner. I don't know if that answers your question. I guess basically I'm saying that you need, if you don't want to stall your pipeline, and you don't want to have a really low clock frequency, you basically need these to be at least 2 deep. Okay? If you go through like what happens if you try to make them 1 deep, it basically just doesn't work, right? Like you basically have to stall the previous thing all the time or every second cycle because you never know if you've got enough room to take what data it's going to send you. But if you have more imbalance, like for example, you've got some DDR that's adding a little bit of imbalance to how long your computation might be cycle by cycle, it can be beneficial to make these bigger. And there's no one answer. So, but they get more and more expensive the bigger you make them. When you put them in RAM, and for the larger FIFOs, this is more area efficient. It's also more power efficient. The reason it's a lot more power efficient is you're writing in 1 word and you're reading out 1 word. The shift register is moving everybody over 1. For big FIFOs, that's a big difference. Okay, so this becomes a lot more power efficient, and you want to do it. In an FPGA, once you use this structure where you're putting it in memory, you have to put it in block RAMs. The block RAMs are certain sizes. They're relatively large. Like usually the smallest block RAMs in an FPGA are maybe, say 18 or 20 kilobits. So that's not enormous, but it's not tiny. What it means is you lose a lot of the pressure to fit it into 2 words. Like, well, if you're going to use the block RAM and it's going to allow you to store 16 words, you might as well store 16 words. Even if it turns out that you think you could do it with 2 or 3, you got 16 for free. Does that make sense? So you get some granularity effects too. Yeah?
When working with CAD tools like Corda, it's very rare for me to actually build a FIFO just use an IP core. Does it do a choice like this? Like, will it choose between 1 and 2 normally, or does it always do 1 or the other?
It depends how you write your HDL, okay? So yeah, you can write all this by hand. You can basically make the memory, make the write pointers and read pointers, but I'll show this to you in like assignment 2. You can also ask for IP cores that are like, build me a FIFO, and now Quartus will build it. And Quartus will actually evaluate building it out of shift registers or building it out of block RAM, and it will choose based on how big your FIFO is what it thinks is more efficient. In your HDL, if you actually write a shift register and it's big enough, Quartus will actually behind your back convert it into this. okay? Which is usually a good idea. It takes a lot less area and a lot less power. It is sometimes bad for timing, okay? So the reason I know that is because, yeah, when I worked at Altera and we get time and closure issues, one of the first things I'd look for is, did they write a big shift register that we converted into a RAM-based FIFO, and is it on their critical path? Because sometimes we wanted to put it back. But yeah, the CAD tools will actually, if you write at the usual abstraction layer, which is they're writing kind of code in HDL that describes a shift register, or you're instantiating FIFO IP, then Quartus will decide what to do automatically. Unless you click on, there are buttons in there saying, don't do anything automatically, I'm telling you to do this, and then it'll obey what you ask for. Yeah?
Yeah, and also the model does give you the option, like if there's like a little pop-down menu, like you want to implement this using VRAM or using like registers. So
Yeah.
it does give you the option.
Yeah, so there are controls in that. They probably have an auto button though too, right? Like,
I can't remember.
no, so in Quartus I loved auto buttons. I just made auto buttons for everything, and then would like, I'd make like, okay, you can override the decisions you want, but yeah, effectively you probably don't know exactly how to use this that well. I think I know better, I'm gonna do it. So the default for everything was like auto, right? But there was the ability to override it if you thought you knew what you were doing. And some people did. Yeah, so good question. You'll see, basically in assignment 1, the interface to your design is essentially this kind of handshaking protocol, right? Where you have a data and valid, and you can back pressure to say, I'm not ready. And in assignment, and you're going to basically make different hardware using different compute models and pipeline it and so on. In assignment 2, it's similar, but now there'll be more data flowing, so you'll also have to think about buffering. So you will use these concepts in assignment 1 and 2, but in something that's not too complicated, because it will make the system really big, it'll get too complicated too fast. Any other questions? Okay, so let's go on to something that also someone asked. So this is, that reconfigurable computing book defines the next data, the kind of next more powerful, but more expensive compute model as streaming data flow with allocation. Which is a very fancy name. Okay, so what does that mean? So it basically adds a little more flexibility to say, well, what if I don't want to have the same sort of spatial pipeline or streaming hardware all the time? What if I want to change it sometimes? So we can change the operators now. You can change the operators or the connections between them. Over time. Okay, so 2 basic ways to do this. First way is kind of the obvious way. You basically build in the FPGA all the operators you might want and all the muxing between them you might want. So the hardware is still kind of static. It's just you've added the ability to, like, you build all the hardware and you just mux between it, basically. Okay, so it allows you to do more flexible computations, but obviously it increases the cost of your hardware. Okay, so you can build extra flexibility in the ops. And build muxing in the interconnect. Okay, so what does this look like? So I might have some operator F1, and maybe I've got another version of it, F1 prime, and I could mux in between those. Then send it off to some G, but I'm going to make my G more general. Okay, so maybe what that means is this G also has some control signals, some extra registers. You know, instead of making just a matrix multiplication unit, maybe it has some control signals that allow it to also do some other operations like vectors and so on. So this got more expensive by being more flexible. And I have this F2 that's always the same. Okay, so let me give you another example. Maybe this G, So in your, like let's say I'm just doing the quadratic equation. And if I always am going to do the same quadratic computation, okay, so let's say I basically say I've got some input x, I'm doing some signal processing, and I'm going to build the coefficients of this quadratic function right into my hardware. So the hardware will actually get more efficient because the synthesis engine basically, when it does this multiplication of x squared times 181, if it actually knows it's 181, it can do logic optimization on it. The way you would multiply this is with a sequence of adds and shifts, if you do it in the logic fabric, and all the multiplications by bits that are 0, it just gets rid of, okay? And the shifts, it can basically just do them all by wiring. So this will be more efficient than a more general G, right, where I load the coefficients. So I could have registers that store A and B and C, and I could compute any quadratic. So now you can change the quadratic I'm computing, but my hardware's a little more expensive. Okay, so if you make your hardware more specific for an FPGA, more specific hardware is generally always a bit more efficient, but an FPGA can get extra efficient because we can do these extra compile time optimizations. So it means, if I didn't need this generality, I'd be better off just hard coding it. But if I need the generality, I build the more general hardware. And then clearly this gives me two options now for this F1 operator that could be totally different. But I had to build both, and I had to build the muxing in between them. So it's at least twice as expensive. Muxing is actually not that cheap. So depending on how big these operators are, it could be noticeably more than 2x as expensive. So basically, these things are expensive in FPGAs. It's done all the time, but you'd really prefer to make your hardware as specific as possible for efficiency. And let's say that if cycle by cycle, sometimes you needed to do F1, sometimes you needed to do F2 or F1 prime, there's not much you can do, right? Like this is what you have to build, because every cycle it might change, so I need to have this control signal be controlled by my data, and kind of think of this whole thing as one bigger, more flexible unit. But there are cases where this doesn't change very often. So one of the big ones that I know about is something called a mux ponder, which is not a word you probably have ever heard of, because I'd never heard of it before I saw these designs either. So I told you that one of the big markets for FPGAs is high-end communication equipments, right? So routers that go across like between big telco exchanges. So from Bell's exchange here to some exchange in Colorado at like super high rates, okay? So all sorts of data comes in from all sorts of line cards all over Toronto. It gets multiplexed together, so at very high data rates until it's at basically optical rates and many different wavelengths, and it's sent out over very high-speed serial I/O and converted by an optical module into usually a whole bunch of wavelengths that are all in a standard called SONET, that are all being modulated at a high frequency, and that's sent out over like fibers to go long distances. Okay, so that piece of equipment is very expensive. Okay, it's taking all sorts of communication protocols from all over the city and various other things, aggregating the data together at very high speed and sending it to optical modules to go over fiber optics. Those boxes, some of them at least, they actually have a lot of different protocols that can go into them because they're taking data from all sorts of other smaller communication networks, say like optical fibers that's connected to your house, and other ones connected to businesses, and DSL lines, and wireless data, and all sorts of stuff. And there's a whole bunch of protocols for that. So it turns out companies like Bell will actually they'll buy these big boxes, and they essentially are selling space on these core routers. These are called core routers. And so they sell it to some company, and maybe it's like Tech Savvy or something, and Tech Savvy wants to connect into it with a certain protocol. So they want, 12 terabits of input data, and they want it on a certain protocol. And every once in a while, Tech Savvy decides like we don't need that much bandwidth, or they don't pay their bills, and Bell's going to kick them off the box, and they're going to resell that space to somebody else. But the other company they want to resell it to wants to use a different protocol. Maybe they want to come in an optical fiber on a different frequency. And so the protocol is different. So they actually need different processing to kind of take that data, figure out what it means, error correct it, and then start muxing it in with all the other data before it goes to the long distance fibers. So what companies like Cisco would have to do is they'd have to build in support for all sorts of protocols. And they know they'll never use them all at once, right? It doesn't even make sense. They can't actually activate all of these input protocols and actually take all the bandwidth and move it to the output. But they don't know in advance which ones they're going to need, and it slowly changes, right, as the customer mix changes and people don't pay their bills. So it seems inefficient, because you know you won't use this and this at the same time. You might use this 1 month, you might use this the next month. But there's like a long time period in between when you're using them. So that kind of leads to the desire for a different model of how could we change with the operators, but we only have to change them slowly. So if we only have to change these slowly, what else could we do? So what do you think? So especially like sit in FPGA. Okay, if it's in an ASIC, you kind of spin another ASIC. Okay, so that's actually even slower. That's not going to help you in a month. What do you think? Yeah, so you can reconfigure, because we could just say, well, don't do this. Have one of them, and then finally after a month, you don't need this anymore. Okay, fine, turn this on. Okay, so one way you could do that is just basically have multiple designs and load different designs in. Because I told you it takes like 100 milliseconds to load a design in. That's not too long. Problem is, so these core routers, they can't do that. The reason they can't do that is part of the guarantee, part of their pricing and their service level agreement to their customers is like, this will not go down, right? This is like the internet for like major companies, right? And the fact that you can reconfigure the FPGA in 100 milliseconds, well, that's not good enough, because to reconfigure the FPGA, usually you have to reset the system, because the FPGA just went crazy for a while. There's a whole bunch of FPGAs in here. So you can't have the system just go mad for like, even a second. So you'd have to reset the system, which means the whole thing comes down for maybe 5 minutes or 10 minutes or something. Everybody loses internet who's on the Bell network. This is just not a good solution. Like it's not acceptable to them. Companies like Cisco have uptime requirements of, they can handle like, their target is less than 5 minutes of downtime a year. And the reason I know that is they would ask all sorts of questions about the reliability of FPGAs, because they would be putting, we'll talk a little bit later in the course maybe about radiation and how they can cause upsets in some FPGAs. They would be putting so many high-end FPGAs into a box that they worried, is radiation flipping bits in this going to exceed my uptime budget? Because I've got like 20 high-end FPGAs in here, and it takes 5 minutes for the system to reboot if something goes wrong, and I'm out of spec if I have more than one reboot a year. So anyway, the reprogramming it for many people would be okay, but for these guys, not okay. At least not reprogramming the whole device where it goes down. So, yeah.
To me, something like priority sort of seems like.
So what do you mean by priority?
So you can have, there's no need to limit, let's say I have a mix, but you can connect, I guess, some priority queue or some priority FIFO that will connect to both modules, and then based on the priority, like if we want F1 to work most of the time, and F1 prime not to work, we can assign F1 to a much higher priority than F1 prime.
So I think you're saying maybe give this more area, this less area, something like that?
Not necessarily, like if they can write to the same buffer, they don't, like, it's just we pull out whatever output that has a higher priority than the other.
Yeah, I guess that's kind of not the problem they're facing right now, though. Like this one will be used or this one will be used. It's that it's this chip real estate. It's the fact that they had to build both and buy a bigger FPGA.
In that case, yeah, one more area than the other.
Yeah, so they could try to balance that, but it's challenging. So, but going back to your comment about like, could you reconfigure? So I guess I'm saying that the most straightforward thing to do would be just reconfigure the whole FPGA, right? But you can't do that. But you're on the right track. Is there anything else you could do? Yeah, so you could partially reconfigure it. So that's the second method, is basically, could I change part of this without taking the system down? So I gave you that long story to give an example of like, this is a system you can't just take down and say, I'll reprogram the whole thing. but there is a significant upside if you could specialize over time to like what's going on. So yeah, the second method is reconfiguring part of the FPGA, which is often called partial reconfiguration. Okay, so what does that mean? So let's just draw it out. It's F1 and F2 going into something G1. And then every once in a while, we might decide, okay, that's not exactly what we want anymore. We're going to change F1 to F1 prime. And we're going to change G1 to G2. And maybe F2 was fine. We didn't need to change it at all. Okay, so we change this piece, and we change this piece. And the whole idea is we did this without taking the whole system down, right? All the IOs are still operating properly. The rest of the design is operating properly. Maybe there's some control logic that figures out I should back pressure everything while this is happening. Like that's actually the typical technique. If you back pressure everything, you reconfigure this. It's pretty fast. If this is a small part of the chip, so if configuring the whole chip takes 100 milliseconds, and I'm only reconfiguring, 10% of the chip, then it takes roughly 10 milliseconds. So it's pretty fast. If I back pressure all the parts of the design that are connected to this, hopefully nobody notices anything because it's pretty fast. So this is a good solution for the case I just gave you, right? That what's called a mux ponder, taking all these high-speed communication traffic on all sorts of protocols, muxing it together, sending it out a high-speed optical fabric. Is this easy to do or not? Yeah, this is hard. Okay, so it's like something people historically academics have really liked. It seems really cool with FPGAs. It's like it's kind of like it's hardware, like not hardware like a processor, but spatial hardware like an ASIC. But we can change it over time. So it is cool, but it is a difficult design flow. It does exist in at least Vivado and Quartus. I'm not sure about other FPGA vendors. So it's a difficult design flow, but the CAD tools do support it. It's just you don't want to do this as like, this is the first design flow I think I'd like to do because it sounds so cool, because it is harder. And the reason I just went through that Mux Ponder case is like, so I was one of the people who architected the Quartus partial reconfiguration solution, and the reason we did it was that design case, right? It was these core routers. For a long time, Altera went, partial reconfiguration, academics love it, but it's not commercially that important. It became commercially important because of that exact case I was talking about, of core routers where they wanted to, core mux ponders, like these aggregation routers, where they wanted to be able to change the protocols without taking the system down. Yeah?
Does this happen on like a module by module basis? Like you tell Vivado, whatever tool, hey, this module, replace it with this module.
Yeah, that's basically it. It's done like module by module. I'll show you like what it is and why it's, well, I'll show you why it's a bit hard, okay? So, because processors do this all the time, right? Processors are doing this without us thinking about it. Like every cycle is doing different instructions. So it's like just fundamentally changing what's going on all the time. So why is this so much harder in an FPGA? Okay, so why is this a difficult design flow? Yeah.
Well, everything around it has like fixed like placement and like routing, so you have to kind of like fit this new module in like the space of the old one.
Right. Yeah. So it is. That's exactly it. Like you have to think about the most difficult part of this is kind of the physical integration. In a processor, you change the instructions. All the instructions are in memory. It's kind of you stick them all in memory. They're all there. It's fine. Here, I want to change from F1 to F1 prime. Well, F1 has to fit in the same space as F1 prime. And that space in an FPGA is not just a region. It's also a region that implies how many RAMs, how many DSPs, how many logic blocks. So I basically have to make that space the larger of these two. Okay, I can always make it bigger so it accommodates both, but this is a constraint. They have to fit in the same physical space. So let's write that down. That's the first one. So F1 prime, this thing that I want to configure in, change it. It must fit in the physical space of F1. Okay, and it means same logic, RAM, DSP, etc. This means two things. You have to think about this. The other thing is it means you also have to floor plan. Most FPGA users like to write logic, so they primarily design in HDL, sometimes even high-level synthesis, and then they like to push the button on the CAD tools, right? And the CAD tools work everything out. Like how do I implement those FIFOs? How do I optimize your logic? Where do I put everything? And that's a big productivity boost versus ASIC tools, which do typically require a lot more guidance. If you are going to do this, you can't leave it to the CAD tools to just say, pick where F1 goes and then pick where F1 prime goes. You have to floor plan to say they both go here, because otherwise it doesn't make sense. You're the only one that knows that I want to be able to take these two things out. So you have to give more guidance to the tool. The second physical thing you have to think about is that this F1 prime and F1 are talking to G. Okay, and in a processor, the way things talk is they talk, through registers and through memory. We are talking through wires. Okay, so that's a much lower level interface. It can be much more efficient, but it means when we take F1 out and we put F1 prime in, it actually has to hook up to the exact same wires for its inputs and outputs that F1 did. So it first means it better have the same inputs and outputs. Like if you just decided I changed my inputs and outputs in my HDL, that doesn't make any sense. But not only that, the CAD tool has to line up. I'm not actually changing where, say, G2 is. Like I'm actually just leaving it there. So if you were hooked up to wire number 10 million to bring a signal in here, when you put F1 prime in, it has to hook up to wire number 10 million. The CAD tools can do that, and they've gotten better at this, so they kind of hide more of that from you, but it basically makes the placement and routing problem harder for the CAD tool, which generally has some impact. Usually the designer notices that as higher probability of routing failure, poor timing, etc. But the tools have gotten better at it. So it used to be a bigger deal than it is now. But basically these interface signals okay, so what your interface is in the HDL has to be the same across those two things that are going to be swapped in, and the physical wires have to be the same. Okay, at the edge of F1 and F2. Oops, F1 and F1 prime must match. This is probably part of, this design flow is harder, but it's probably not as hard as, it's not nearly as hard as it used to be. The early generations of this, which were done by Xilinx, they were the first ones to do partial reconfiguration. I mean, basically the designer had to handle this, right? So you can imagine how painful that is when you're trying to line up the wires. Now the CAD tools handle it for you, so it's kind of hidden from you. It's just the CAD tool has to work harder. Yeah?
So for the interface signals, like what happens to the wires between F1 and G? Do they go high resistance for a while while you reprogram it, or do they
Yeah.
store the last bit before you just click the button? What happens?
Yeah, so that's the next thing, actually. So you need to think of what happens while you're reconfiguring, because, okay, so maybe it takes 5 or 10 milliseconds. It's not that long, but it's a lot of clock signals. So during those clock signals, you have to have come up with something, some plan that your system doesn't just go mad, right? That you don't have these there's a bunch of random ones and zeros on this, these signals, and this G module maybe is an output module, and it's happily sending packets all around the world with like complete gibberish, right? Or error packets, or reconfigure the internet packets, and like you can imagine, or subtract this from my bank account packets. Like, like you can imagine the design engineers doing this. If you say like, yeah, for 5 milliseconds, your system, we have no idea what it's doing, right? But what's the worst that could happen? Like, probably they could think of a lot of things that would happen badly. So, okay, so F1 prime, this new, okay, so the outputs of this F1 and F1 prime, whichever one we've got in there right now, they are the inputs to some other module. So inputs to G. They must go to some reasonable state. And this latency, the latency insensitive design model we just talked about kind of gives us a hint. Like a reasonable state would mark everything as on your inputs or on your outputs, basically, everything that you're outputting, basically mark it as invalid. So set all the valids to 0. And on your inputs, your back pressure signals, mark them all as your back pressure. So, you know, that protocol actually gives us a hint of what would be reasonable. Say I can't do anything and I haven't given you any reasonable data. So that would be a reasonable state. The tools have gotten better at helping you with this too. This is, again, a pretty low-level thing. It's not enough that just logically you think of what I should like to have to happen. As the new configuration is being written in, you need to think all of my valid bits go to 0, all my back pressure bits go to 1, and they stay there. They don't start waving, toggling around. So the latest generations of the Vivado and Quartus CAD tools do make that easier, where they kind of work out, this is how we will reconfigure it, this is how we will hook up your wiring so that we can guarantee that. And it is actually a bunch of work for the CAD tool, but it was even worse for the designer. But the designer at least needs to think about, what is the protocol? Like, what do I want to happen, even if the CAD tools help make that happen? Yeah?
So program the FPGA, you go like row by row and column by column, so you probably can set all the valid bits to 0 and all the back pressure bits to 1 at the exact same time. So
There's a couple ways to do this. One is you can put a little ring around the region you're reconfiguring, and that ring is essentially like putting AND and OR gates on those signals, and you don't reconfigure it. Okay? So you can have a signal that goes into it that says reconfig started, and all the signals actually coming out of your module, which have this little halo around it, now will stay at valid as 0 and back pressure as high. Does that make sense? So that's one way you can do it. And it's kind of the dominant way to do it, right? So the other thing is that modern FPGAs, you can write kind of arbitrary regions. So I know Altera's device is the best, but I think Xilinx ones are similar now. While you write entire rows, basically, I showed you the configuration circuitry, you sort of shift in, and then you write, like, say, an entire row or an entire column. In the really big chips, you might write a piece of a row or a piece of a column, but it's the same idea. What Altera did, and I think Xilinx has this now too, is they also have mask registers. So with a mask register, you can basically say, don't write these ones. And what that allows you to do is you can now do arbitrary regions. Does that make sense? Even though the programming hardware is built to kind of write an entire column at a time, if you also have a mask register, it essentially disables all the writes outside of where you wanted. And if you step that through a whole bunch of columns, you can now write an arbitrary piece of data. So that took away like kind of constraints on what do the region sizes look like. Let's see. Okay, and then the last thing is that reconfig is fairly slow, which is a fundamental thing you have to figure out for your applications. Does this make sense? For some applications, it's too slow. You just can't do it. And how slow? It's basically a reasonable rule of thumb for a big FPGA is about 100 milliseconds times the percent of the chip. Okay? This could be made faster, right? If you devoted more IOs and so on, you could make this faster. So maybe it'll get somewhat faster in the future. It's a little bit of a chicken and egg problem because unless people use this feature much, the vendors aren't super keen to spend hardware on it. But if people use it more, then they'll spend a bit more hardware on it. Okay, so I want to go quickly through a few, maybe I'll just wipe all this stuff off, and I'll quickly go through a couple optimizations, and then we'll be done for today. Okay, so streaming optimization. So we already talked about this a bunch, so I'm not going to belabor it further, but pipeline. Okay, so registers are plentiful in FPGAs. They're pre-built, so you're kind of there for free until you get to quite high numbers. So it's probably the number one optimization approach. Let's say I've done that. Okay, so I've got some logic here. Let me draw it out. Okay, so I've got a couple of registers feeding a LUT, feeds another register. Which feeds a chain of LUTs. And another register, and the same thing happens down here. Okay, so let's say I pipelined my HDL, and I got this. I got a bit of logic between these registers, but a lot of logic between these registers. So the delay between this register and this one is 2 nanoseconds. Between that one and this one is 6 nanoseconds. Okay, so I'm going to be limited by this 6 nanoseconds, right? That's going to be my minimum clock period. So clearly I could have done a better job of pipelining this, but it can take a while to figure out exactly where to put pipeline registers in your HDL to get them in the right spot. And sometimes it's not obvious. Like in your HDL, you don't see lookup tables, right? So you don't necessarily know that there's going to be more logic on this side than that side, because you're kind of writing at a slightly higher level of abstraction. And so it can be difficult to balance perfectly. So an optimization that can be done both by the CAD tool, and you can actually apply it yourself mechanically on your HDL, is retiming. Okay, so people know what retiming is? Have you heard of this? Okay, one person. Anybody else? Who has not heard of retiming? Just to get, okay, so quite a few. So that sounds good. Okay, so somebody who knows what retiming is, why don't you take a shot at explaining it? And I promise I actually know what it is. And that always it raises the question, wait, you don't know? But I do know. Rafael, what is it?
So basically, it looks at all of your logic, and then it basically shifts the registers in the path of the logic to kind of I think it balances the delay time, basically.
Yeah, so retiming is a speed optimization. It moves registers to basically try to balance your pipeline. Okay, so it knows that this 6 nanoseconds is a problem, and it wants to move registers to shorten the critical path. So that's its goal. What it guarantees is that from the outside of the circuit, you can't tell it's been done. It does not change any of the functionality of the circuit, and it does not change the latency of the circuit. So it's not visible to a user. It can be safely done. Does that make sense? If you go inside the circuit, what is in this register could change. But from the IOs of the circuit, you can't tell it's been done. That's why a CAD tool can actually do it automatically. So in Quartus and Vivado, you can turn retiming on and off. And it's also a technique that you can just apply by hand. So if you know about it, you can just do it in your own HDL sometimes. Yeah?
I guess with retiming, do you have to maintain the same number of registers?
No. It will change. Well, it will keep the same number of registers on a path, so it will not change latency, but in terms of the number of registers in the design, it will change. Does that make sense?
Yeah, because I was wondering if you move, let's say, going on the line between this
Yeah, I'll show you a retiming on this. So let's see, what would a retiming algorithm do here? Okay, so retiming basically can move registers forward or backwards. Across logic. And its purpose is to basically to balance timing paths, like to shorten the critical path. And this can be done automatically. Or you can do it by hand. Okay, and the reason it can be done automatically is it's not observable at the IOs. Okay, so CAD tools won't pipeline automatically. The reason they won't pipeline automatically is it's observable, right? The latency of the system has changed. And they don't know if that's okay, right? Maybe you needed that latency, or maybe there's some higher level protocol they don't understand. So they don't automatically pipeline, not at the HDL level, right? So you can take a higher level specification like HLS, where you don't know where the clocks are, and you can say, well, I can pipeline that because nobody knows where the clocks are, right? You didn't put them in yet. But in HDL, where you have the clocks, tools won't automatically pipeline, but they can automatically retime because you can't tell it's been done from the outside. Yeah?
So CAD tools are able to find all of the retiming opportunities, or?
They try. So no, they will never find them all, because CAD tools aren't perfect. So that's why I said you can also do this by hand, because if CAD tools were perfect, you'd never have to do much by hand, but they're not perfect. Does that make sense? So I'll show you what a CAD tool would do with this. So it would basically it looks at this register, and it sees that there's worse timing on the right side than the left, so it wants to move it across this logic. And what retiming does is it does local transformations. So instead of having this register here, I can do what's called a forward retime, where I move the register over the fan out in its output. Okay? But when I do that, I'm going to get 2 copies of this register. And that basically maintains the latency of all my paths. So I can't move this register just here. I have to take 2 copies of it, put one here, one here. So this circuit would be transformed into, well, maybe I'll just cross that out, and I would have a register here and a register there. Okay? And if I did that, I might wind up with something where I get 4 nanoseconds here and 4 nanoseconds there. So it's faster. And from the outside world, I can't tell this has happened. The functionality is the same, and in fact, the latency is also the same. Whereas if I repipelined it, the latency would change. Yeah?
The way we drawn it here with lookup tables, so it will just turn off the optional flip-flop we have at the end of each left, or over there, turn them on over on the right side.
Yeah. So.
Read out at the same time.
Yeah, so depending on how your architecture works, in many FPGAs, there is a register and a lookup table kind of grouped together. So you're right, it would not use that register and use these ones. So there's also, even though I've got 2 registers here, it might not actually add any significant cost because I had 2 available. That's not the only thing. Retiming can also do backward moves. So if this was really slow, like if I basically, these interconnect delays were really slow and this path was longer, this register could have been moved back here instead. And that would have been fine too. The way I've drawn this, that seems unlikely that would be a good idea, but it evaluates both of those. And it doesn't evaluate it for one register. It goes through your whole design, evaluating it for all the registers, and it iterates a few times. So does this mean that so what this means is instead of carefully pipelining your design, I could just say, I'm not going to put that register there. I'm just going to put 2 registers at the start and no registers in the middle. In fact, I love retiming. I'm going to put 10 registers at the start and then no registers anywhere else in my data path. And you can do that. And if the CAD tool was infinitely smart, it would be fine. But you are putting a lot of pressure on the CAD tool, right? It's not infinitely smart. So this is probably not a great idea because you've kind of moved far away from an optimized solution and you said, can you get back to it? it's smarter to kind of put the pipeline registers in what you think are reasonable spots and then let retiming fine tune it. And again, it also can be a useful way to think about looking at my timing reports. I don't like where my registers are. Instead of rethinking my whole data path, I can just think of it as just local operations, because that can, in a complicated data path, it can also be easier to think about that. So you can do this too, where you change your HDL a little bit at a time, where you're effectively doing retiming manually. You can turn this on and off. For a long time, this was off by default in Quartus. Now it's on by default, because there are so many registers in the latest Altera chips, they really want to use retiming aggressively. But you can turn it off. And I don't know if it's probably on by default in Vivado too. Why do you think you'd ever want to turn this off? Like, there are reasons why you'd want to turn this off, actually. So what do you think? Do you have an idea?
It's not good enough, and like this takes too much time in compile.
So compile time's one. That's a good idea. Not good enough. I mean, that would mean it's actually degrading your circuit, which is possible, but as a former CAD engineer as well, I kind of feel bad that you don't trust the tools, although that happens. But yes, but there's another reason. It's not the CAD engineer's fault, and I love those reasons. So yeah, what do you think?
Maybe it's difficult to debug, I guess, hardware logic issues.
Yeah, so there's a really important reason you turn this off, which is if you're trying to debug it. So FPGAs, one of the advantages they have over ASICs is better debugging tools. You can actually read out their registers while the design's running. You know, you can stop the design, you can read out the registers. You can embed logic analyzers, so you can actually, the major FPGA vendors all have tools to put in what are called embedded logic analyzers. So you watch these registers, and on this condition, I want you to trigger and capture all the data and then send it to me. Okay, if this retiming was done, from the outside I can't tell, but I had a register here, and now I got two registers here. And I don't know what those registers are capturing, right? Like, it's not anything I wrote in my HDL. It's capturing some processed data. It all works out. You know, the CAD tool went through all the logic and it made sure it makes sense. But if you get this back in a debug viewer, you're just like, what is that, right? That's not the signal I put in there. So if you turn it off, it makes debugging easier with those tools. Okay, so the last optimization I was going to show you is there are some IP blocks that can be faster than a single stream. Let's see how much time I have. Okay, I have 2 minutes. Got to go fast. Okay, so let's say, so this probably wouldn't happen. Where this can happen is you're using IP blocks that you bought or they're in the vendor tools, and maybe they run it for 400 megahertz and the rest of your design runs at 200. Okay, so they're kind of over-engineered for what you need. But maybe you actually have multiple streams of data. Okay, so you're processing data at 200 megahertz, but you've actually got a bunch of channels, right? Like a whole bunch of antennas that you're processing. So if you have an IP block that runs at 400 megahertz, it has twice the throughput. Maybe you could actually use it for 2 streams. So you can do that by time domain multiplexing these IP blocks. Okay, so you're going to send in, one piece of data from stream A, then one piece of data from stream B, then stream A again, and so on. You're going to make use of the extra throughput. It could be a pain to figure out on the output side, well, which data goes to which stream, because you'd have to know the latency, and maybe the latency is not constant or well documented. So some of the vendor IP blocks will actually have an extra little bit of data, which is basically a tag. So you can tag the data with the stream ID. Okay, so what does this look like? So you've got some function A, you've got some function B. These are both maybe 200 megahertz, and we wrote them at our company. They're putting data into a FIFO, so they're both dumping data into this FIFO. And then there's some IP block that we bought. It's made by some superstar designer. It takes a lot of area, so we kind of would like to not instantiate too many of them. But it actually runs really fast, 400 megahertz. And basically, if we've tagged our streams with A and B, and this IP block was written to expect that, on the output side, we'll get like the tags A and B, and we can use that to decide where to put it. So we can have a FIFO A and a FIFO B, and put them in those. So this is something that some of the high-end signal processing IP from Altera does. It does tag the data with streams, and therefore you could run the IP block at its maximum frequency and take the streams apart on the other side. People also do this with some of the hardened blocks in an FPGA. Things like DSP and RAM blocks sometimes run faster than the parts of the design that they put in the lookup tables and the registers. So sometimes people do this themselves, where they just take a bunch of DSP blocks and run them 2 times as fast, for example, and they'll do time-domain multiplexing and demultiplexing on the 2 sides of it. Yeah?
Does it have to be like a clean, like integer multiple of clock speed, or?
Yeah, that's a good question, actually. I guess it works nicer in my example with the clean integer multiple. I guess it doesn't have to be, right? There's really no, if you're sticking stuff in this FIFO and your logic out front can just interleave it, this doesn't really care, right? It's just got a bunch of data. So I don't think it does, but I guess I'm not 100% sure. I'd have to look at individual IP blocks to see if they had that constraint or not. Yeah?
I had a similar point, like in this case, how often, like air of caution, you will still have asynchronous FIFOs where the read and write clocks are.
Yeah, so this FPGAs, normally their blockrams have a read port and a write port, and you can put them on different clocks. So FPGAs are actually very good at like FIFOs that do clock domain crossing. So yeah, this one you'd be writing in at twice the width, but half the frequency, and reading out at half the width, but twice the frequency. And FPGA blockrams are very good at that because they have 2 ports, and the read and the write port can be run at different clocks. Okay, that's it for today. Thanks, everybody.